There is a moment that happens at many ancient sites just before excavation begins. From the surface, the place looks ordinary, just rock, sand, forest, or empty land. Then something appears. A buried wall, a hidden staircase, the outline of a forgotten structure beneath the earth. And suddenly an entire lost world begins to emerge from silence. Some discoveries reveal civilizations no one expected. Others expose tunnels, chambers, and monuments that challenge the historical timeline around them. What makes ancient mysteries so fascinating is that many of them were hidden in plain sight for centuries. The evidence was always there. People simply did not realize what they were standing on. And even now, countless parts of the ancient world may still remain buried, waiting for the moment they are uncovered again. The ancient region of Gandhara, where summer temperatures can exceed 40 degrees Celsius and seasonal humidity destroys organic material within decades, produced something almost impossible: fragile birch bark manuscripts still readable after nearly 2,000 years. These texts, discovered near Hadar and Taxila, were written centuries before most surviving European manuscripts even existed, and yet many retained visible ink, flexible fibers, and structural integrity that modern conservation scientists still struggle to explain. In the 1990s, several sealed clay jars containing tightly rolled birch bark scrolls surfaced from ancient Buddhist monastic sites in the Gandharan region. Radiocarbon dating later placed some manuscripts between the 1st century BCE and the 2nd century CE, making them among the oldest surviving Buddhist texts ever discovered. What shocked researchers was not only the age of the manuscripts, but the condition they remained in despite being made from one of the least durable writing materials imaginable. Birch bark is an organic material composed primarily of cellulose, hemicellulose, and lignin. Under ordinary environmental conditions, those compounds degrade rapidly through oxidation, fungal invasion, insect activity, and moisture absorption. Modern untreated bark exposed to fluctuating humidity can begin structural breakdown within only a few years. Even museum-preserved bark samples often become brittle after several decades. Yet many Gandharan manuscripts survived for almost 2 millennia. Compared to Egyptian papyrus, birch bark should theoretically perform worse in unstable climates. Papyrus survives mainly in hyper-arid desert environments where humidity remains extremely low. But the Gandharan manuscripts endured seasonal temperature variation, underground moisture, and microbial exposure. Some fragments still retain flexibility today. Conservation teams examining the scrolls found fiber layers that had not completely crystallized or collapsed, something rarely seen in ancient cellulose-based materials of comparable age. This has created one of the strangest material science mysteries in archaeology. How did ancient scribes stabilize a biodegradable surface so effectively that it could outlast medieval parchment in some cases? This is where the mystery becomes far more difficult to explain. Modern laboratory studies confirm that birch bark naturally contains betulin and suberin, compounds that provide limited water resistance and antifungal properties. However, those natural defenses alone are nowhere near strong enough to account for survival across 2,000 years. Under normal burial conditions, microorganisms penetrate cellulose layers, causing irreversible fragmentation. Fungal hyphae usually spread rapidly through organic writing surfaces, especially when trapped underground. But several Gandharan scrolls display surprisingly little deep fungal penetration. Microscopic analysis revealed that some bark surfaces behaved almost like treated composite material, rather than raw organic bark. The outer layers appear unusually compacted, while certain internal fiber structures show signs of controlled thermal alteration. Researchers suspect the bark may have undergone a deliberate stabilization process involving oils, resins, smoke curing, mineral salts, or low-temperature heating. The problem is that no surviving ancient text explains the method. Some conservation scientists have proposed that ancient craftsmen may have used plant oils similar to linseed or cedar extracts to reduce water absorption. Others suspect alkaline mineral treatments that altered the pH balance of the bark surface, slowing microbial growth. A few chemical traces even suggest possible resin coatings comparable to primitive varnishes. If true, this would mean Gandharan craftsmen understood empirical preservation chemistry centuries before the development of formal material science. What makes the mystery even stranger is the uniformity of preservation. These manuscripts were not isolated anomalies. Multiple scrolls from different locations show similar resistance patterns, implying the existence of a standardized production method rather than accidental preservation. Some experts compare the phenomenon to Roman hydraulic concrete. For centuries, historians believed Roman concrete durability was accidental until mineral analysis revealed complex volcanic chemical reactions inside the material. The Gandharan manuscripts may represent a similar case, a lost technological process hidden inside a seemingly primitive artifact. There is also evidence that the scrolls were intentionally stored inside controlled microenvironments. Many were sealed in clay jars with extremely limited airflow. Some jars may have contained organic desiccants capable of reducing internal humidity. This effectively created a primitive climate control system nearly 2,000 years before modern archival storage. Even today, major libraries preserve ancient documents at humidity levels between 30 and 50% to prevent fungal growth and fiber collapse. The Gandharan monks may have discovered practical versions of the same principles entirely through observation and experimentation. The writing itself presents another unresolved puzzle. Most ancient inks degrade aggressively over time. Iron gall ink, widely used in medieval Europe, often destroys the paper it was written on through acid corrosion. Carbon-based inks are more stable, but they usually sit on the surface and gradually flake away as the material beneath deteriorates. The Gandharan manuscripts behave differently. Spectroscopic analysis indicates the use of carbon black mixed with plant gums and trace minerals. But unlike ordinary surface ink, portions of the writing appear partially integrated into the bark fibers themselves. Instead of cracking off, many characters remained sharply visible, even after severe physical fragmentation of the scrolls. Some scientists believe the bark surface may have been chemically prepared before writing, allowing controlled capillary absorption without excessive spreading. In modern terms, this resembles a primitive primer layer used in high-end archival printing. If accurate, the implication is astonishing. Ancient scribes may have engineered both the writing surface and the ink as a unified preservation system. The manuscripts also reveal extraordinary manufacturing consistency. Many strips were cut with near identical width and thickness. Whole alignments used for threading remain remarkably straight over long sections. Line spacing often appears geometrically controlled despite being written entirely by hand. This level of standardization raises difficult questions about production tools. At the time these scrolls were created, the region lacked the industrial cutting systems associated with later manuscript cultures. Yet some bark sheets show cleaner preparation than early medieval European parchment. The surfaces appear carefully flattened without catastrophic fiber tearing, something difficult to achieve even with modern manual processing. Several researchers have argued that workshops producing manuscripts in Gandhara may have operated at a far more organized technical level than previously assumed, possibly involving specialized artisans trained specifically in bark treatment and document preservation. One of the strangest parts of the mystery is that the technology seems to vanish from history. Later manuscript traditions across Central Asia, India, and Europe rarely match the same level of preservation. Many medieval papers degraded faster than the Gandharan birchbark scrolls despite being far younger. This suggests the process relied on specialized knowledge that may have disappeared through invasions, political collapse, or the destruction of monastic communities. History has seen similar losses before. Roman concrete formulas vanished for centuries. Damascus steel became impossible to reproduce after medieval trade networks collapsed. The birchbark manuscripts may represent another forgotten technology, one that appeared simple, but depended on an advanced understanding of materials and preservation far ahead of its time. Do you think the survival of the birchbark manuscripts was simply ancient craftsmanship, or evidence of a lost preservation technology far ahead of its time? Share your thoughts in the comments below. The Altai Mountains of eastern Kazakhstan, close to the borders of Russia, Mongolia and China, hide one of the strangest burial sites ever discovered: beryl burial mounds. Inside these stone-covered tombs, archaeologists found horses with intact skin and hair, wooden saddles that never rotted away, and organic materials preserved for more than 2,000 years beneath solid ice. What should have turned to dust survived almost perfectly, and the deeper researchers studied beryl, the more impossible the site began to look. The beryl kurgans were first documented during Russian expeditions in the 19th century, but the most important excavations began in 1998 under Kazakh archaeologist Zainola Samashev. Beneath massive stone mounds scattered across the Beryl Valley, researchers uncovered elite tombs belonging to the Scythian Saka nomads of the 4th to 3rd century BCE. One burial chamber immediately shocked scientists. Inside were 13 horses laid side by side with elaborate ceremonial decorations still attached to their bodies. Their leather harnesses, wooden ornaments, felt coverings, and even patches of fur had survived because the tomb had frozen solid shortly after burial. Permafrost preservation is known in Siberia, but beryl was different. The tombs appeared engineered to create and maintain freezing conditions deliberately. That possibility transformed the site from a remarkable archaeological discovery into a technological mystery. Among all the mysteries of beryl, none is more controversial than the preservation of organic materials. Under normal conditions, leather, fur, wood, and textiles decay rapidly because of bacteria, moisture, fungi, and oxygen exposure. In temperate climates, untreated leather can begin breaking down within decades. Yet at Beryl, materials older than 23 centuries remained astonishingly intact. The immediate explanation was ice, but laboratory analysis showed preservation quality that exceeded what freezing alone should achieve. Some horse remains retained structural collagen stability far beyond expectations. Wooden components preserved microscopic carving details that normally disappear even in permanently frozen environments. Researchers discovered traces of resins, oils, and organic coatings on some artifacts. Chemical studies suggested mixtures derived from tree sap, animal fat, and plant compounds may have been intentionally applied before burial. Several compounds displayed antimicrobial properties comparable to primitive preservation treatments. The exact formulation, however, remains unknown. This has led to one of the most debated theories surrounding beryl. The Saka elites may have possessed an advanced empirical understanding of organic preservation centuries before formal chemistry existed. Comparisons with other frozen burials make the anomaly even stranger. The famous Pazyryk burials in Siberia, located roughly 500 kilometers away and culturally related to beryl, also preserved organic materials through ice formation. However, some beryl artifacts demonstrated lower bacterial degradation rates despite similar environmental conditions. That difference suggests additional preservation methods may have been involved. Modern conservation laboratories still struggle to recreate the same level of long-term stability in untreated natural materials. Museums storing ancient leather often require controlled humidity between 45 and 55%, temperatures below 20 degrees Celsius, and continuous chemical stabilization. Beryl achieved preservation lasting more than 2,000 years without modern technology. Some scientists believe the tomb builders intentionally manipulated airflow, moisture penetration, and thermal insulation using layers of stone, timber, and packed earth. Others argue the preservation was accidental, but enhanced by unknown organic treatments. Either explanation implies a far more sophisticated understanding of environmental control than historians normally associate with nomadic cultures. The mystery becomes even deeper when considering the horses themselves. Their bodies were not simply buried. They appear carefully prepared before interment, with evidence suggesting ritual cleaning and possible treatment of the skin and harnesses. Some scholars compare the process to early forms of mummification, though entirely different from Egyptian techniques. Unlike Egypt, where natron salts dehydrated the dead, burial preservation relied on freezing and environmental isolation. Two civilizations separated by thousands of kilometers may have independently developed completely different methods for defeating decay. The burial mounds themselves represent a major engineering puzzle. Some burial kurgans exceed 30 meters in diameter and contain thousands of tons of stone transported into mountainous terrain without wheeled transport or advanced machinery. The tomb chambers were built from massive larch logs arranged with geometric precision. Above them, layers of stone created thermal insulation while also trapping moisture that later froze. Researchers believe meltwater seeped downward during seasonal temperature changes, then became trapped beneath the stone layers where winter temperatures froze it permanently. What fascinates engineers today is how stable the internal environment remained. Freeze-thaw cycles normally destroy underground structures over centuries. Expanding ice fractures stone, collapses cavities, and rots timber. Yet Beryl's chambers survived with remarkable structural integrity. Some modern geotechnical specialists have compared the design principles to passive thermal regulation systems used in Arctic engineering today. By carefully controlling density, airflow, and insulation layers, the builders may have unintentionally or intentionally created stable cryogenic chambers. If deliberate, this would mean Iron Age's nomads understood long-term environmental engineering at a level never previously attributed to them. The horses of Beryl remain among the most visually haunting discoveries in archaeology. Each animal was buried wearing ceremonial masks, decorated with gold leaf, carved wood, and symbolic animal forms combining deer, mountain goats, birds of prey, and mythological hybrids. The craftsmanship is astonishingly precise. Some gold foils are less than 1 millimeter thick yet contain highly detailed engravings. Producing such decorations required advanced metalworking control and specialized artisan skill. Even more mysterious is the arrangement of the horses. They were positioned with extraordinary uniformity, all facing the same direction inside carefully organized burial rows. This suggests strict ceremonial protocols, possibly linked to cosmology or elite military symbolism. DNA studies indicate many of the horses were selectively bred. Their skeletal structures reveal animals optimized for endurance and mountain mobility rather than brute strength. This implies controlled breeding programs among Saka elites over centuries. The burial of 13 horses alongside a single elite individual also represented immense economic sacrifice. In nomadic societies, horses were survival assets. Killing so many valuable animals for one funeral demonstrates extraordinary social hierarchy and ritual importance. Artifacts found at Beryl reveal connections stretching across Eurasia. Chinese silk fragments, Persian-influenced decorative techniques, and steppe animal-style art appeared together within the same tombs. This suggests the Altai region participated in long-distance exchange systems centuries before the Silk Road formally emerged during the Han Dynasty around the 2nd century BCE. The scale of this interaction raises difficult questions. How did isolated mountain nomads maintain communication and trade across thousands of kilometers? How were fragile luxury materials transported through extreme terrain? And how did artistic styles spread so rapidly across ancient Eurasia without centralized empires controlling the routes? Some historians now view the Eurasian steppe not as an empty barrier between civilizations, but as a highly active technological corridor connecting distant cultures long before classical trade networks were officially recorded. Do you think the people of Beryl possessed knowledge far beyond what history officially recognizes? Share your thoughts in the comments below. The southern coast of Aliki ancient marble quarry was carved apart directly above the Aegean Sea. Massive white marble blocks weighing more than 20 tons were extracted from cliffs so close to the water that some of the quarry now lies underwater. Even today, archaeologists still cannot fully explain how ancient workers cut, polished and transported stone with a level of precision that seems dangerously unrealistic for the tools officially available at the time. The site was first systematically documented during 19th century archaeological surveys of Thasos, though local fishermen had known about the submerged quarry remains for centuries. Divers later discovered unfinished marble blocks beneath shallow seawater, tool marks preserved in submerged stone, and quarry channels carved directly into the coastal rock. These discoveries revealed that Aliki was not a small regional quarry. It was an industrial-scale marble extraction complex that supplied some of the most important construction projects in the ancient Mediterranean during the Greek and Roman periods. What makes Aliki extraordinary is not simply the amount of marble removed. It is the sophistication of the engineering hidden inside the quarry itself. The entire operation appears optimized with an efficiency that resembles a pre-industrial production system, rather than a primitive extraction site. The marble of Thasos was among the purest in the ancient world. Modern mineralogical analysis shows that Thasian marble contains exceptionally high calcite purity, often exceeding 98% calcium carbonate. This gave the stone its famous luminous white appearance and unusually strong light reflectivity. Roman elites considered it one of the finest decorative stones in the empire, comparable to the famous Carrara marble later used during the Renaissance. But purity also created a major technical problem: highly crystalline marble fractures unpredictably under stress. Extracting large intact blocks without modern machinery should have been extraordinarily difficult. Yet the quarry walls at Aliki contain long extraction channels cut with astonishing consistency. Some grooves run for several meters in nearly straight lines, with remarkably uniform depth. Even modern stonemasons studying the site have noted how difficult it would be to reproduce such precision using only handheld iron tools. Unlike rough quarry marks commonly seen in ancient extraction sites, many cuts at Aliki appear methodical and geometrically controlled. The standard explanation claims workers used iron chisels and wooden wedges. According to this theory, narrow slots were carved into the marble, dry wooden wedges were inserted, and water was added until the expanding wood generated enough pressure to split the stone apart. The method is historically documented in several ancient cultures, but experiments performed on dense marble blocks have shown that the process is highly unstable. Pressure often spreads unevenly through crystalline stone, producing uncontrolled fractures. At Aliki, however, many extracted blocks remained remarkably intact despite their enormous size. Some unfinished blocks still visible at the quarry may have weighed between 15 and 25 tons. Separating stone masses of that scale without catastrophic cracking would require precise understanding of natural stress lines, crystal orientation, and internal weaknesses within the marble. Ancient quarry workers may have possessed practical geological knowledge far beyond what historians traditionally assume. Even more mysterious is the location of the quarry itself. Most ancient extraction centres were established inland where workers could operate safely and move stone gradually toward transport routes. Aliki was carved directly beside steep coastal cliffs exposed to sea wind and wave erosion. Some extraction surfaces descend almost into the water itself. This suggests the quarry was intentionally designed around maritime transport from the beginning. But that creates another unsolved engineering problem. How are multi-ton marble blocks lowered onto ships without modern cranes? No large harbour infrastructure survives at the site. No permanent lifting towers have been found. And the terrain is so uneven that conventional dragging methods would have been extremely dangerous. Some archaeologists believe ancient engineers built temporary wooden ramps coated with lubricants such as animal fat or wet clay to slide blocks downward. Others propose the use of compound pulley systems, similar to those described centuries later by Roman engineers like Vitruvius. Yet none of these theories fully explains the scale of extraction visible at Aliki. The logistical challenge becomes even more astonishing when compared with other ancient quarrying sites. At the Roman granite quarries of Aswan in Egypt, unfinished obelisks demonstrate how difficult hard stone extraction could become, even with enormous labour forces. In contrast, Aliki's marble appears to have been removed with far cleaner separation surfaces and less evidence of catastrophic failures. Unlike granite, marble is softer, but its crystalline structure makes large-scale precision extraction extremely unpredictable. The consistency achieved at Aliki suggests highly refined quarrying techniques developed over generations. But perhaps the greatest mystery of all involves the finishing of the marble itself. Ancient writers described Thasian marble as glowing under sunlight. Modern optical analysis partially confirms those accounts. Because of its calcite composition and low impurity content, polished Thasian marble reflects light deep beneath its surface before scattering it outward again. This creates a soft luminous effect similar to subsurface scattering seen in human skin. It is one reason ancient Greek and Roman sculptures made from high-quality marble appeared almost lifelike under natural light. The problem is that many surviving Thasian marble surfaces exhibit levels of smoothness extremely difficult to achieve with ancient polishing methods. Under microscopic examination, some polished sections reveal abrasion patterns consistent with ultrafine finishing compounds. The surface roughness in certain samples approaches levels associated with advanced polishing abrasives. Officially, ancient craftsmen used sand, emery powder, crushed quartz, and leather polishing techniques. Emery from the island of Naxos was especially prized because of its hardness. However, reproducing the mirror-like finish observed on some Thasian marble, artifacts would have required enormous labour and exceptional consistency. This raises a disturbing possibility. Ancient craftsmen may have understood mineral abrasives and surface finishing chemistry far better than surviving texts suggest. Some researchers speculate that fine polishing pastes containing silica-rich compounds or microscopic abrasive particles may have been used systematically. Others suggest prolonged wet polishing with progressively finer abrasives could gradually reduce surface imperfections to near microscopic levels. What makes the mystery even deeper is durability. Many Thasian marble surfaces retained their brightness despite centuries of exposure to humid sea air and salt erosion. Normally, salt crystallization gradually destroys polished stone surfaces over time. Yet some marble from Aliki still preserves remarkable reflectivity after nearly 2,000 years. This suggests the finishing process may have altered the stone surface in ways not fully understood today. The quarry also contains abandoned blocks frozen mid-extraction, as if work suddenly stopped. Some remain partially attached to the bedrock with extraction grooves already completed around them. Historians debate why the site was eventually abandoned. Economic collapse during the late Roman period may have reduced demand. Earthquakes could have destabilized coastal operations. Pirate raids were common in the Aegean during periods of imperial decline. Rising sea levels may also have submerged parts of the transport system itself. That final possibility is particularly important. If ancient loading platforms, ramps, or harbour structures now lie underwater, then the most critical evidence explaining how Alaki functioned may still be hidden beneath the Aegean Sea. Divers have already identified submerged quarry surfaces extending below modern sea level, suggesting that portions of the industrial complex disappeared gradually beneath the water over centuries. Do you think the lost technology of Aliki was simply forgotten over time? Or was it far more advanced than historians are willing to admit? Share your thoughts in the comments below. Northern Vietnam, near the Ma River and Dong Son archaeological site, became the centre of one of the most disturbing technological mysteries in the ancient world. Archaeologists uncovered bronze drums so advanced that some researchers still struggle to explain how they were made more than 2,000 years ago. These were not simple ritual objects. Some weighed over 100 kilograms, carried perfectly symmetrical geometric patterns, and produced deep resonant tones comparable to precision-tuned instruments. Yet they emerged from a society traditionally described as a late Bronze Age culture, without writing, advanced machinery, or industrial infrastructure. The deeper researchers studied the Dong Son drums, the more disturbing the technological gap became. The first major discoveries began in the late 19th century during French colonial excavations in northern Vietnam. Local villagers had already been finding buried bronze objects near riverbanks and rice fields for generations, but systematic excavation revealed something unexpected. Enormous ceremonial drums covered in incredibly detailed imagery, cast in single pieces using techniques that even modern foundries consider difficult without precise thermal control. By the early 20th century, hundreds of drums had been identified across Vietnam and throughout Southeast Asia, stretching from southern China to Indonesia. Their existence suggested that a powerful metallurgical tradition had once dominated the region long before recorded local history fully emerged. The greatest mystery surrounding the Dong Son drums is not their artistic beauty. It is the manufacturing technology itself. Some of the finest examples, including the famous Ngok Lu drum, measure roughly 79 centimeters in diameter and stand more than 60 centimeters tall. The walls remain remarkably thin and consistent, despite the immense size of the object. Modern metallurgists understand how difficult this should have been. Bronze casting on such a scale creates enormous thermal stress. If the molten alloy cools unevenly by even a small margin, cracks form instantly, especially in large hollow objects. Ancient furnaces also lacked modern temperature sensors, controlled airflow systems, and industrial crucibles. Yet many Dong Son drums survived intact for over 2 millennia. Researchers studying the alloy composition found that the drums were not made from simple copper. The metal mixture often included carefully balanced percentages of tin and lead, sometimes varying slightly between sections of the drum. These variations appear intentional rather than accidental. Higher tin concentrations increase hardness and resonance, but also make bronze more brittle. Lead improves fluidity during casting, allowing molten metal to flow into extremely detailed molds. Too much lead, however, weakens the final structure. Somehow, Dong Son metalwork has achieved a balance sophisticated enough to produce objects that were both durable and acoustically resonant. What makes this more difficult to explain is the sheer scale of the casting process. Most Bronze Age societies cast objects in smaller components before joining them together. Large single-piece castings were exceptionally risky because the entire mold could fail during cooling. Yet many Dongson drums appear to have been cast as single units. Experimental archaeologists attempting reconstructions found that reproducing similar drums required enormous quantities of charcoal, highly stable furnace temperatures exceeding 1000 degrees Celsius, and precise timing during pouring. Even slight interruptions cause structural defects. Some modern researchers have openly admitted surprise that such consistency could be achieved without advanced mechanical systems. The surface decorations deepen the mystery further. The center of many drums contains a multi-pointed star surrounded by concentric geometric bands. Around these rings appear warriors, birds, boats, dancers, and animals arranged with astonishing radial symmetry. On certain drums, dozens of repeating figures maintain nearly identical spacing across the entire circumference. Creating such precision on a curved mold surface without advanced measuring tools should have been extraordinarily difficult. Several engineers who examined high-resolution scans of Dongson drums noted that some pattern deviations are so small they fall within tolerances comparable to early mechanical drafting techniques. Yet no compasses, rotating calibration devices, or precision marking instruments associated with the culture have ever been found. One theory suggests artisans used rope-based geometric systems combined with rotating carving platforms, essentially primitive mechanical lathes. Another theory proposes generations of specialized craftsmen developed highly refined proportional methods through apprenticeship. Neither explanation fully accounts for the mathematical consistency seen on the finest drums. The acoustic properties of the drums remain another unresolved puzzle. When struck, certain Dongson drums produce low-frequency resonance capable of carrying long distances across open landscapes. Acoustic testing performed on surviving drums showed complex harmonic behavior influenced by wall thickness, internal volume, and the raised star-shaped center. In some cases, the vibration patterns resemble those of tuned bells or ceremonial gongs from far later periods. This has led some researchers to question whether the decorative reliefs were purely symbolic. Raised patterns on modern instruments often affect resonance by redistributing vibrational stress across the surface. Certain Dongson motifs may have unintentionally or deliberately modified sound behavior. If intentional, it would imply an empirical understanding of acoustics developed centuries before formal acoustic science existed. The distribution of the drums across Southeast Asia introduces another technological mystery. Hundreds of Dongson-style drums have been discovered far beyond northern Vietnam, including Laos, Thailand, Cambodia, Malaysia, and Indonesia. Some were transported across mountainous terrain or vast maritime routes. Considering that larger drums could exceed 100 kilograms, their movement required organized trade systems and logistical coordination far more sophisticated than traditionally assumed for the region during that era. Archaeologists now believe maritime networks across Southeast Asia may have been active centuries earlier and on a larger scale than previously thought. Certain drums found in Indonesia display local modifications while preserving core Dongson manufacturing principles, suggesting either technological transfer or direct trade contact over enormous distances. This raises a difficult question. Was Dongsun merely a regional culture, or the center of a much larger metallurgical network that has mostly vanished from history? Another mystery lies in the extraordinary preservation of the drums themselves. Northern Vietnam's tropical climate is extremely hostile to metal. High humidity, acidic soils, and seasonal flooding accelerate corrosion rapidly. Yet many drums retain sharp engraving details after more than 2,000 years underground. Metallurgical analysis suggests stable oxidation layers formed across the surface, protecting the inner bronze from steeper decay. The precise alloy ratios may have unintentionally created corrosion-resistant properties similar to controlled patina formation, seen in some modern engineered bronzes. Even more intriguing is the symbolic language engraved onto the drums. The recurring birds, solar patterns, ritual scenes, and boats appear too structured to be random decoration. Some scholars believe the imagery encoded cosmological beliefs, agricultural cycles, or political authority systems. Others suggest the drums functioned as ceremonial communication devices linking distant communities through shared symbolic language. The star motif at the center remains especially debated. While often interpreted as a sun symbol, its geometric dominance and repeated numerical structure suggest it may have carried more complex meaning tied to astronomy or ritual timing. The technological gap becomes clearer when compared to neighbouring cultures of the same period. Around the time many Dongsun drums were being produced, large parts of Europe were still creating far simpler bronze objects with less precise decorative symmetry. Even some early Chinese bronze traditions relied heavily on sectional mould assembly rather than enormous thin-walled castings. The Dongsun drums therefore do not fit neatly into the expected technological hierarchy of the ancient world. Do you think the Dongsun civilization discovered a level of metallurgical knowledge far ahead of its time, or are we still missing a major piece of the story? Share your thoughts in the comments below. Inside the ruins of Preah Palilei, massive trees crush ancient stone walls that should have collapsed centuries ago, yet the temple still stands. Built on unstable tropical soil nearly 800 years ago, surrounded by humidity, floods, roots, and erosion, Preah Palilei survives in conditions that destroy most stone structures within a fraction of that time. Archaeologists studying the site discovered something disturbing. Many of its engineering solutions resemble concepts used in modern structural stabilization, and nobody fully understands how the Khmer Empire achieved them without advanced machinery, modern surveying tools, or reinforced concrete. Unlike Angkor Wat, Preah Palilei remained largely isolated for centuries beneath dense Cambodian jungle growth inside Angkor Thom. French explorers and archaeologists working for the École Française d'Extrême Orient documented the temple during the late 19th and early 20th centuries as they began clearing large sections of Angkor. What they found was not a massive ceremonial complex, but a strangely quiet temple with unusual structural features, steep stairways, hybrid religious iconography, and foundations that appeared far more sophisticated than expected for the period. The greatest engineering mystery surrounding Preah Palilei is not the visible temple itself, but what lies underneath it. The entire Angkor region sits on highly unstable tropical ground, affected by monsoon cycles, seasonal flooding, shifting groundwater, and compressible sediment layers. Modern engineers consider this type of environment extremely difficult for heavy masonry construction. Even today, buildings constructed on weak saturated soil often require deep reinforced foundations, concrete piles, or soil stabilization systems to prevent uneven settlement. Yet the Khmer Empire built enormous stone monuments here nearly a millennium ago. Geological studies across Angkor have shown that Khmer builders frequently used layered laterite, compacted sand and sandstone blocks arranged in carefully engineered sequences beneath temple platforms. At Preah Palilei, this foundation system appears unusually effective. Despite centuries of root invasion and structural stress, major sections of the temple remain standing, What makes this so mysterious is the apparent understanding of load distribution. Some structural engineers comparing Angkorian construction techniques to modern concepts have suggested that Khmer builders unintentionally developed primitive forms of floating foundation systems. Instead of forcing structures onto rigid, deep supports, they created wide, stabilized platforms that distributed weight across soft terrain. This approach resembles principles now used in modern geotechnical engineering. The comparison becomes even more striking when examining environmental pressure. Cambodia's tropical climate receives roughly 1,500 to 2,000 millimeters of rainfall annually. Tree roots in jungle environments generate enormous mechanical force over time. Certain tropical species can split concrete, asphalt, and modern retaining walls within decades. Yet parts of Praia Palele survived centuries of direct root compression. Some sandstone blocks remain aligned despite trees physically growing through the structure. This creates one of the biggest unanswered questions in Khmer engineering. How did builders without modern geology understand how to prevent catastrophic foundation collapse in one of the most destructive construction environments on Earth? The stairways at Praia Palele are unusually steep, even compared to other Khmer temples. Certain sections approach angles that modern public safety standards would consider impractical or dangerous. The common explanation is symbolic. The ascent represented movement from the human world toward the divine realm. But symbolism alone does not explain the engineering challenge. Constructing extremely steep stone staircases in tropical conditions is structurally risky. Water erosion rapidly weakens exposed edges. Weight concentration increases stress fractures. Small design errors can destabilize entire stair sections over time. Yet many of Praia Palele's stairways retain recognizable geometry after centuries of weathering. Researchers comparing Angkorian architecture with Mesoamerican pyramids have noted surprising similarities in elevation symbolism and steep ceremonial ascent. However, there is no evidence of contact between the civilizations. The resemblance may instead suggest that ancient societies independently discovered similar architectural solutions for monumentality and religious psychology. Still, the precision required to maintain balance and symmetry on such steep inclines without modern mathematical instruments remains difficult to explain fully. Several stone joints at Praia Palele display extremely tight fitting between sandstone blocks. In certain areas, gaps are thin enough that even modern blades struggle to pass through them. This is one of the most controversial recurring mysteries in ancient architecture worldwide. Similar precision appears in Inca masonry at Sacsayhuaman in Peru, granite construction at Giza in Egypt, polygonal stonework at Ollantaytambo, and certain Roman imperial structures. The Khmer Empire primarily relied on iron tools, manual labor, and basic lifting systems. Yet sandstone surfaces at Praia Palele often appear flattened and aligned with remarkable consistency. Modern stoneworkers note that high-precision fitting usually requires repeated surface grinding, accurate measuring systems, controlled cutting angles, and stable transport methods. But Khmer builders operated inside dense tropical forests under extreme humidity and heat. Even more puzzling is transportation. Some sandstone blocks used throughout Angkor weigh multiple tons and originated from quarries near Phnom Kulen, over 50 kilometers away. Transport likely relied on canals, rafts, elephants, rollers, and manpower. However, no definitive reconstruction fully explains how such large-scale logistical precision was consistently maintained across the empire. Praia Palele contains signs of multiple religious transitions layered directly into its structure. Earlier Khmer architecture was heavily influenced by Hindu cosmology, especially Shaivism and Vishnu worship. Later phases of Angkor shifted increasingly towards Mahayana Buddhism and eventually Theravada Buddhism. At Praia Palilei, these transitions appear physically embedded into the temple itself. Some carvings reflect classical Hindu iconography, while others contain Buddhist imagery associated with later centuries. The result is a structure that looks almost architecturally divided across time. Normally, temples rebuilt centuries apart reveal obvious inconsistencies in engineering and alignment. But several sections at Praia Palilei connect with surprising structural continuity. This suggests one of two possibilities. Either Khmer engineers preserved highly standardized construction knowledge for generations, or their architectural systems were far more mathematically organized than historians once believed. Perhaps the strangest mystery is not how the temple was built, but why it still exists. Tropical environments are devastating for sandstone. High humidity accelerates chemical weathering. Biological organisms penetrate porous surfaces. Constant rainfall weakens mineral bonds. Modern conservationists at Angkor continuously battle deterioration. Yet, some carvings at Praia Palilei remain visible after centuries of exposure. Microscopic analysis of Angkorian sandstone has revealed variable resistance depending on mineral composition, porosity, and grain bonding. Certain blocks appear significantly more resistant to erosion than expected. This has led to theories that Khmer builders may have intentionally selected sandstone with unusually durable mineral structures. Others speculate they possess surface treatment methods now lost to history. No definitive answer exists. What is clear is that many surviving Khmer structures continue outperforming what modern researchers initially predicted they should survive. What do you think the Khmer Empire truly understood about engineering and construction that may have been lost to history? Share your thoughts in the comments below. Northern Yucatan, Mexico. Beneath a landscape with almost no rivers, the ancient Maya built a city that may have survived for over 1,000 years by engineering an invisible water system beneath solid limestone. At the center of it stood Zibil Chaltun, a city whose roads ran in unnatural straight lines, whose buildings aligned with the sun to near-perfect precision, and whose survival still raises questions modern archaeology cannot fully answer. Unlike lost jungle cities swallowed completely by rainforest, Zibil Chaltun was never entirely forgotten by local communities. Formal archaeological investigation began in the 1940s, but the major excavations were carried out during the 1950s and 1960s by the Carnegie Institution and Mexican archaeologist E. Willis Andrews IV. What researchers uncovered was shocking. A massive Maya urban center covering nearly 20 square kilometers, potentially housing more than 20,000 people at its peak between 600 and 900 AD. That immediately created a paradox. Northern Yucatan possesses almost no permanent surface rivers. Annual rainfall averages roughly 700 to 1,000 millimeters, but the porous limestone ground absorbs water rapidly. Large populations should not have been sustainable here for centuries. Yet Zibil Chaltun flourished. The most famous structure at Zibil Chaltun is the Temple of the Seven Dolls, a relatively small building compared to the pyramids of Chichen Itza or Tikal. But its mystery may be even greater. Twice each year during the spring and autumn equinoxes, the rising sun passes directly through the temple's aligned eastern and western openings with astonishing accuracy. Thousands still gather there to watch the event today. The phenomenon is so precise that even small structural deviations would have destroyed the alignment centuries ago. What makes this difficult to explain is not merely that the Maya track the sun. Many ancient civilizations observed celestial cycles. The real mystery is the engineering precision achieved without metal surveying equipment, telescopic optics, magnetic compasses, or modern geometry tools. Researchers studying Mesoamerican astronomy have noted that the sun's position at sunrise changes gradually throughout the year. To create an alignment that works repeatedly over centuries, builders needed to determine the exact east-west solar axis with extremely low angular error. A deviation of only 1 or 2 degrees could ruin the effect entirely. The Maya also faced another challenge rarely discussed: horizon distortion. The apparent rising position of the sun changes depending on atmospheric refraction, terrain elevation, and seasonal visibility conditions. Modern archaeoastronomers often use computerized calculations to reconstruct ancient alignments. Yet the Maya achieved this using observational methods alone. Some archaeologists argue the structure functioned as a ceremonial solar calendar tied to agricultural cycles. Others believe it was part of a much larger astronomical network spread across the Yucatan Peninsula. Similar solar alignments appear at Chichen Itza, Uxmal, and Mayapan, but the alignment at Zibilchaltyn remains unusually minimalistic and mathematically direct. Inside the temple, archaeologists discovered 7 unusual clay figurines with exaggerated features, giving the structure its modern name. Their purpose remains unknown. No definitive Maya text explains who they represented or why exactly 7 figures were hidden there. Some theories connect them to cosmology or ritual astronomy, but there is still no consensus. The deeper mystery is psychological as much as technical. The structure demonstrates that the Maya were not merely watching the sky casually, they were embedding astronomical calculations directly into architecture with repeatable long-term precision. In practical terms, the building itself functioned almost like a stone instrument. Zibilchaltyn existed because of water, specifically because of a massive natural sinkhole called Slaka Cenote. Unlike civilizations built beside visible rivers like the Nile or Euphrates, the Maya of northern Yucatan depended on hidden groundwater trapped beneath limestone bedrock. Cenotes formed when underground caves collapsed, exposing freshwater reservoirs connected to vast subterranean systems. The Slaka Cenote at Zibilchaltyn measures roughly 40 meters wide and more than 40 meters deep in some sections. Archaeologists discovered offerings, ceramics, jade objects, tools, and human remains inside, suggesting it was both a water source and sacred site. But the real puzzle lies in how the city was planned around it. Satellite mapping and excavation data show that many residential and ceremonial sectors were positioned to optimize access to groundwater and seasonal runoff. The Maya appear to have understood the hydrological behavior of porous limestone terrain with surprising sophistication. Modern hydrologists studying karst systems use geological modeling, groundwater mapping, and remote sensing technologies. Yet the Maya identified sustainable settlement zones over 1,000 years ago with no known advanced instruments. Even more impressive is the city's long-term survival. Population estimates suggest Zibilchaltyn may have supported tens of thousands of inhabitants for centuries. That required consistent freshwater access despite periodic droughts that devastated other Maya cities. Some climate studies indicate that parts of the Maya collapse around the 9th century coincided with prolonged megadroughts lasting decades. Sediment cores from Yucatan Lake suggest rainfall reductions of up to 40% during severe episodes. The mystery is why Zibilchaltyn survived longer than many inland centers, despite existing in one of the most water-sensitive regions of Mesoamerica. Zibilchaltyn was connected by raised white stone roads called Sakbeob. Some extended for kilometers with remarkably consistent orientation. From the air, certain routes appear unnaturally linear, almost as if they were planned using modern surveying techniques. Maintaining straight alignments through dense tropical terrain is difficult even today without optical references. The Maya had no pack animals capable of heavy transport and no practical wheeled freight system. Every stone block, construction material, and trade good had to be carried manually. Yet the city expanded into a vast urban network linked with regional trade routes stretching toward the Gulf Coast. Obsidian from highland Guatemala, marine shells, jade, and imported ceramics have all been discovered there. This suggests logistical organization on a scale far beyond the stereotypical image of isolated jungle settlements. Another unresolved mystery is the durability of Maya construction materials. Most structures at Zibil Chaltun were built using limestone masonry coated with lime plaster. Producing lime requires heating limestone to temperatures exceeding roughly 800 to 900 degrees Celsius, a process demanding enormous quantities of fuel. For a city this size, the amount of wood required would have been staggering. Yet many structures still retain bonded masonry after more than a millennium of humidity, storms, heat, biological growth, and erosion. Some material scientists studying Maya mortar have identified traces of organic additives that may have improved strength and water resistance. In certain tests, ancient lime plasters displayed microstructural resilience, unexpectedly competitive with some later historic mortars. The engineering contradiction is difficult to ignore. A civilization supposedly limited technologically managed large-scale thermal material production, long-distance logistics, astronomical calibration, and sustainable urban planning simultaneously. What do you think really caused the fall of Zibil Chaltun? Was it drought, collapsing trade networks, internal conflict? Or is there still something about this ancient city we have completely failed to understand? Share your thoughts in the comments below. The ancient region of Angkor in present-day Cambodia holds one of the strangest engineering mysteries of the Khmer Empire. Baksay Chamkrong rises from unstable tropical ground like a stone anomaly. More than 1,000 years ago, Khmer builders constructed a steep brick pyramid in one of the wettest regions of Southeast Asia, and somehow made it survive heat, monsoon rain, invasive jungle roots, and centuries of erosion. The greatest mystery is not its size, it is the technology hidden inside it. Baksay Chamkrong was built during the 10th century under King Harshavarman I and later completed by Rajendra Varman II. The temple remained largely overshadowed by larger monuments such as Angkor Wat and Bayon, even though it sits near the royal core of Angkor. Early French archaeologists from the École Française d'Extrême-Orient documented and restored parts of the structure during the early 20th century after thick jungle growth had partially consumed the monument. What researchers found beneath the vegetation was not simply another Khmer temple, but a compact engineering structure filled with unusual construction techniques. The most famous unexplained feature of Baksay Chamkrong is its brickwork. Thousands of red bricks were fitted together with a level of precision that still confuses engineers today. In many sections, the joints between bricks are so thin they are almost invisible to the naked eye. Even thin metal blades struggle to slide between some blocks. This becomes difficult to explain when compared with ordinary medieval brick production. Ancient bricks were usually inconsistent in shape because kiln temperatures fluctuated heavily. Even Roman bricks, among the finest of the ancient world, often show visible mortar layers several millimeters thick. At Baksay Chamkrong, however, some joints appear almost seamless. The biggest question is the binding material. Modern cement did not exist. Traditional lime mortar alone cannot fully explain the near-fused appearance of the walls. Chemical analysis conducted on Khmer brick monuments has detected traces of calcium compounds, silica, organic residues, and plant-based substances inside the joints. Some researchers suspect the Khmer may have used natural resins or organic adhesives derived from tropical plants, later hardened by heat and humidity over centuries. Others argue the builders may have polished or ground the brick surfaces after placement to create tighter fits. Yet no confirmed reconstruction has successfully replicated the exact appearance and durability of the original joints. The precision becomes even more mysterious considering the environment. Cambodia experiences intense thermal stress. Surface temperatures on exposed stone and brick can exceed 50 degrees Celsius under direct sunlight, followed by rapid cooling during monsoon storms. This repeated expansion and contraction normally fractures masonry over time. Modern concrete structures in tropical climates often require maintenance within decades. Baksay Cham Krong has endured for more than 1,000 years. Some material scientists believe the clay source itself may hold the answer. Certain Khmer bricks contain unusually high concentrations of iron and silica, which may have produced stronger vitrification during firing. If kiln temperatures exceeded approximately 900 to 1,000 degrees Celsius, parts of the clay structure could partially glassify, dramatically increasing durability. The problem is that achieving and maintaining such temperatures consistently in the 10th century would have required far more advanced kiln control than historians previously assumed for the Khmer Empire. The result is a paradox. A civilization without industrial machinery produced brick joints and weather resistance that remain difficult to duplicate precisely today. Another major mystery lies beneath the temple itself. Angkor sits on soft alluvial soil saturated with groundwater for much of the year. Modern engineers still face severe foundation problems in similar terrain throughout Southeast Asia. Yet Baksay Cham Krong's core structure has remained standing for over a millennium despite its steep pyramid design. The secret appears to involve laterite, the iron-rich stone used inside much of the temple's core. Laterite behaves unusually compared with ordinary rock. When freshly cut from the ground, it is relatively soft. Once exposed to air, oxidation causes the material to harden significantly over time. Khmer engineers may have intentionally exploited this property. But the real puzzle is drainage. Water pressure destroys many ancient pyramids from the inside as trapped moisture expands and weakens internal layers. Researchers examining Khmer construction techniques believe microscopic voids between laterite blocks may have acted as passive drainage channels, allowing water to escape naturally rather than accumulate. In effect, the temple may have functioned like a breathable structure centuries before modern moisture control engineering existed. Some conservation specialists compare this principle to porous architectural systems used in certain modern flood-resistant buildings. The difference is that Baksay Cham Krong achieved this with pre-industrial materials and without modern geology. The geometry of the temple raises additional questions. Baksay Cham Krong is aligned almost precisely along the east-west axis, despite being constructed without modern surveying equipment. For a 10th century structure in tropical jungle terrain, the directional accuracy is remarkable. This has led some historians to suggest Khmer architects possessed more sophisticated astronomical observation methods than previously believed. Like many Hindu temples, the pyramid symbolized Mount Meru, the sacred cosmic mountain in Hindu cosmology, but symbolic meaning alone does not explain the structural mathematics involved. The staircase angles are extremely steep, approaching levels that increase both construction difficulty and collapse risk. Yet the load distribution has remained stable for centuries. Engineers studying stepped pyramids often note that tiered geometry naturally redirects gravitational force downward and outward, reducing concentrated stress. The Khmer may have understood these principles intuitively through experimentation, long before formal structural mechanics existed. Comparisons are often made with Mesoamerican pyramids such as those of the Maya. However, Maya pyramids were usually constructed in drier climates using limestone cores and thick stucco coverings. Baksay Cham Krong faced tropical humidity levels that frequently exceed 80%. Surviving under those conditions is significantly more difficult. The logistics behind the temple remain another unresolved problem. Some laterite and sandstone blocks weigh hundreds of kilograms. The Khmer Empire had no engines, cranes, or industrial transportation systems. Dense jungle and seasonal flooding made overland transport extremely difficult. Researchers believe Angkor's massive hydraulic network may have provided the solution. The Khmer constructed one of the largest pre-industrial water management systems in human history, including reservoirs, canals, and artificial waterways stretching for hundreds of kilometers. Satellite imaging and LiDAR scans have revealed enormous hidden infrastructure beneath the forests surrounding Angkor. Some archaeologists suspect building materials for temples like Baksay Chamkrong were transported partially by water through these canal systems. If true, this would mean the Khmer Empire operated a level of logistical coordination rivaling some early industrial societies. Yet the exact methods remain unknown. No surviving Khmer texts fully describe the engineering process. Perhaps the greatest mystery is simply survival itself. Many Khmer monuments suffered catastrophic deterioration from vegetation, earthquakes, looting, and climate exposure. Tree roots regularly split stone blocks apart across Angkor. Heavy monsoon cycles weaken foundations year after year. Despite this, the core of Baksay Chamkrong still stands. Structural engineers believe the pyramid's layered design may distribute weight more efficiently than flat platform temples of the same era. The steep geometry channels force downward through progressively smaller terraces, reducing internal stress concentrations. Combined with laterite drainage and unusually durable brickwork, the structure effectively became a self-stabilizing system. That possibility changes how historians view Khmer engineering. Instead of relying purely on a massive labor, the builders may have possessed sophisticated empirical knowledge about materials, water behavior, heat resistance, and long-term structural balance. Do you think the builders of Baksay Chamkrong possessed engineering knowledge far beyond what historians believe today? Or are these mysteries simply the result of lost construction techniques? Share your thoughts in the comments below. Rocky highlands across Maharashtra, India, preserve ancient marble quarries carved directly into volcanic stone, still holding marks that should not exist. Long before industrial saws, before steel rail systems, before precision mining equipment, someone extracted enormous blocks of stone here with a level of control that continues to disturb archaeologists and engineers alike. Some cuts run in nearly perfect parallel lines. Some quarry walls appear unnaturally flat, and in several areas, the stone itself carries microscopic evidence of exposure to temperatures difficult to explain using known ancient technology. The quarries were gradually documented during regional archaeological surveys connected to temple construction studies across Western India. Researchers investigating the origins of stone used in medieval Deccan temples notice similarities between quarry marks and finished architectural blocks found dozens of kilometers away. Geological analysis linked several temple stones to quarry zones within Maharashtra's ancient extraction networks. What began as a simple sourcing investigation slowly turned into a deeper mystery involving lost engineering knowledge, unexplained thermal effects, and transportation methods that remain poorly understood. One of the first anomalies is the precision of the extraction itself. Marble is softer than granite, but many quarry sections are surrounded by extremely dense basalt from the Deccan Traps, one of the largest volcanic formations on Earth. Basalt typically measures around 6 on the Mohs hardness scale, significantly harder than copper and difficult even for primitive iron tools. Yet some quarry faces contain grooves that maintain remarkably consistent depth and spacing over several meters. In modern stone-cutting operations, this type of regularity usually requires guided mechanical systems. Traditional archaeology proposes that ancient Indian quarry workers relied on hammerstones, iron chisels, wedges, and controlled fracture techniques. Wooden wedges inserted into narrow slots could be soaked with water, expanding slowly until the rock cracked along predetermined lines. Similar methods were used in ancient Egypt at the Aswan quarries. But certain marks in the Maharashtra quarries appear far more uniform than what repeated hand strikes would normally produce. In some zones, partially detached blocks show separation lines so straight they resemble machine-assisted cuts. Engineers studying ancient quarrying methods have compared these surfaces to Roman imperial quarries, where advanced iron saws combined with abrasive slurry were capable of cutting hard stone with surprising precision. Yet the scale here complicates the explanation. Some extracted blocks may have weighed between 20 and 40 tons based on surviving dimensions, comparable to medium-sized megaliths transported in ancient Mediterranean civilizations. That creates the second major mystery: movement. The Deccan Plateau is not forgiving terrain. Many quarry routes cross steep volcanic ridges, fractured lava fields, and seasonal river valleys. Even modern heavy transport equipment struggles in parts of the region during monsoon conditions. Yet ancient builders somehow transferred gigantic stone blocks across these landscapes long before paved infrastructure existed. Researchers have found unusually flattened pathways near certain extraction zones, raising speculation that ancient transport corridors may once have existed. Some surfaces appear intentionally leveled rather than naturally eroded. Similar theories surround the transportation ramps near Baalbek, where Roman builders moved stones exceeding 800 tons. In both cases, the engineering challenge is not simply lifting the stone, but controlling friction, slope stability, and momentum across uneven terrain. Experimental archaeology has demonstrated that large stone blocks can be moved using sledges, rollers, ropes, and coordinated labor forces. In 1997, Japanese experiments recreating pyramid construction showed that teams of several hundred workers could move multi-ton stones using wooden sledges over prepared surfaces. But scaling that system to mountainous basalt terrain becomes far more difficult. Some quarry locations in Maharashtra sit at elevations where maintaining stable transport routes would require advanced planning and long-term engineering coordination. Still, none of those puzzles are as controversial as the thermal evidence. Several quarry sections contain stone discoloration patterns and altered crystal structures suggesting exposure to intense localized heat. Marble itself begins undergoing visible structural changes under sustained high temperatures. Calcite crystals can recrystallize, weaken, or shift in color depending on heat exposure and mineral impurities. In microscopic analysis performed on ancient quarried stones from comparable sites worldwide, heat-altered zones often indicate temperatures exceeding several hundred degrees Celsius. The conventional explanation is fire setting, an ancient mining technique used by Romans and possibly much earlier civilizations. Workers would build intense fires directly against the rock face, heating the stone rapidly before shocking it with cold water. Thermal stress would weaken the structure, making it easier to fracture. Archaeological evidence confirms the technique existed in ancient copper and gold mines across Europe and Africa. But the Maharashtra quarries contain patterns that some researchers consider unusually selective. Instead of widespread random heat damage, several areas show concentrated thermal alteration precisely along extraction lines. In some cases, the heat appears strongest near fracture initiation points, almost as if workers deliberately targeted structural weaknesses within the rock. Modern quarry engineers know that controlling heat distribution inside stone is extremely difficult without advanced understanding of material behavior. Uneven heating typically causes chaotic cracking, yet parts of these ancient quarry walls display relatively controlled separation patterns. This has led to speculative theories that ancient quarry workers may have possessed highly refined empirical knowledge of thermal fracturing. Not industrial technology in the modern sense, but centuries of accumulated experimentation, allowing them to predict how different stones would react under heat stress. Similar debates exist around the vitrified forts of Scotland, where entire stone walls appear partially melted under temperatures exceeding 1,000 degrees Celsius. Ancient people clearly understood fire better than historians once assumed. Some independent researchers push the idea further. They point to microscopic smoothness along few fractured surfaces and argue the stone may have been exposed to temperatures beyond normal fire-setting capabilities. Others strongly reject this interpretation, noting that volcanic environments, mineral chemistry, and centuries of weathering can distort surface appearance. No evidence of advanced fuel systems or furnaces has been discovered at the quarries, yet the thermal anomalies remain difficult to dismiss entirely. Another unsettling detail is the presence of abandoned blocks. Across the quarry zones, enormous partially extracted stones still remain attached to the bedrock. Some were cut on multiple sides but never removed. Others appear nearly complete, as though work suddenly stopped mid-operation. This mirrors mysteries seen at the unfinished obelisk, where a massive granite monument was abandoned after developing structural cracks. In Maharashtra, the reasons remain uncertain. Geological instability is one possibility. A hidden fracture inside a giant marble block could make transport impossible. Political collapse is another theory. Quarry systems depend on centralized organization, labor, food supply, and long-distance logistics. If regional dynasties weakened or trade routes shifted, entire extraction networks may have been abandoned almost overnight. But some archaeologists suspect environmental disruption played a role. Sediment accumulation around several quarry sectors suggests episodes of rapid erosion or landslide activity. The Deccan region experiences intense monsoon cycles capable of destabilizing entire slopes. A single catastrophic season could have buried transport routes and rendered extraction economically impossible. What makes the mystery more compelling is the architecture built from these stones afterward. Temples throughout Western India display astonishing stone precision. Certain joints between blocks remain tight enough that, even after centuries of seismic activity and erosion, knife blades barely fit between them. Pillars exhibit rotational symmetry difficult to achieve without highly disciplined shaping techniques. Some carved ceilings maintain geometric alignment across enormous spans. At sites like Ellora Caves, builders removed an estimated 200,000 tons of rock directly from volcanic cliffs to create entire temple complexes carved top-down into the mountain itself. The Kailasa temple alone may have required the removal of nearly 400,000 tons of stone. Modern engineers still debate how ancient workers maintained structural accuracy while excavating such massive volumes without catastrophic collapse. The rugged hills of Seriphos ancient mines in the Aegean Sea conceal the remains of mining and metallurgical systems that appear centuries ahead of their time. Deep tunnels cut through extremely hard rock, massive slag fields showing signs of unusually high smelting temperatures, and strangely efficient ventilation systems have led some researchers to question whether ancient miners on this isolated Greek island possessed a level of practical engineering knowledge far beyond what history normally attributes to the Bronze and early Iron Age Mediterranean. The mines were known in antiquity, but systematic archaeological study only accelerated during the 19th and 20th centuries when industrial mining operations on Seriphos reopened old shafts and uncovered layers of ancient workings buried beneath later excavations. Archaeologists soon realized that some tunnels dated back more than 2,000 years before modern mining returned to the island. Pottery fragments, charcoal remains and slag deposits suggested continuous exploitation from at least the early Bronze Age through the Classical and Roman periods. Yet the deeper researchers explored, the more difficult it became to explain how such complex mining systems were created with supposedly primitive technology. One of the greatest mysteries surrounding Seriphos is the geometry of its underground tunnels. Many passages maintain remarkably consistent dimensions across long distances, despite being carved directly into metamorphic rock formations. In several areas, tunnel inclinations remain surprisingly uniform, something difficult to achieve even with modern surveying tools inside confined underground environments. Ancient miners theoretically relied on oil lamps, hammerstones, bronze chisels, and later iron picks. But some shafts descend at angles so controlled that modern mining historians have compared them to organized Roman-era engineering projects developed centuries later. Even more puzzling is the apparent understanding of structural stress inside the mines. Certain pillars were intentionally left standing to support ceilings, and many of these support columns are positioned almost exactly where modern geological analysis would recommend. Seriphos sits within a tectonically active region of the Aegean Basin, where earthquakes have repeatedly shaken the islands for thousands of years. Yet numerous ancient chambers survived remarkably intact. Some tunnels remained stable for over 2 millennia before modern collapses occurred after industrial interference. This suggests the miners possessed a highly advanced practical understanding of rock behavior, fracture lines, and load distribution, despite having no known mathematical models of structural engineering. But the most controversial mystery involves the metallurgical evidence discovered around the island's ancient smelting zones. Large slag heaps scattered across Seriphos contain mineral structures indicating extremely high smelting temperatures. Laboratory analysis of certain iron-rich slag samples revealed partial vitrification and crystal formations associated with temperatures exceeding approximately 1200 degrees Celsius. For comparison, traditional open charcoal furnaces from many early Mediterranean cultures typically struggled to sustain temperatures much beyond 1000 to 1100 degrees Celsius consistently. Reaching beyond 1200 degrees required extremely efficient oxygen flow and highly controlled combustion conditions. This becomes difficult to explain because Seriphos itself is relatively barren. Unlike heavily forested mainland regions, the island lacked the vast timber reserves normally required to fuel large-scale high-temperature metallurgy over centuries. Ancient smelting on such a scale should theoretically have consumed enormous quantities of charcoal. Researchers have estimated that producing a single kilogram of workable iron in early antiquity could require several kilograms of charcoal depending on furnace efficiency. Yet the archaeological evidence suggests sustained production over very long periods. Some researchers believe the miners and metallurgists of Seriphos may have exploited the island's intense seasonal winds to create naturally pressurized furnace systems. Certain furnace remains appear strategically positioned along slopes exposed to strong Aegean airflow. Experimental archaeologists have proposed that carefully angled furnace mouths could have generated a primitive natural blast effect, dramatically increasing combustion temperatures without mechanical bellows. If true, this would represent a surprisingly sophisticated understanding of aerodynamics and thermal engineering for the ancient world. The theory becomes even more intriguing when compared to later blast furnace principles developed much farther north in medieval Europe. Medieval blast furnaces relied on sustained oxygen injection to reach temperatures high enough for large-scale iron production. At Seriphos, there is evidence suggesting ancient metallurgists may have discovered simpler environmental methods to achieve partially similar thermal effects over 1,000 years earlier. No reconstruction experiment has perfectly reproduced the slag signatures found on Seriphos using only conventional Bronze Age furnace designs. Some slag samples also contain unusually low levels of unprocessed iron residue, suggesting highly efficient extraction rates. This implies that the metallurgists were not merely reaching high temperatures accidentally. They may have possessed refined control over smelting conditions and ore preparation techniques. Certain ore fragments appear intentionally sorted before processing, possibly indicating an early understanding of mineral grading. Waste deposits on the island are often layered systematically rather than dumped randomly, implying organized industrial procedures rather than crude extraction. Another mystery involves the mine ventilation systems. Deep underground mining presents a major danger due to heat buildup, oxygen depletion, and toxic fumes. Modern underground operations rely heavily on engineered airflow systems. Yet at Seriphos, some shafts appear positioned in ways that create passive air circulation through temperature and pressure differences between tunnel openings at different elevations. Researchers studying airflow simulations inside portions of the ancient mine network found that some tunnels could naturally channel cool air downward while expelling hot air upward through secondary openings. This passive ventilation mechanism resembles principles later formalized in industrial mine engineering. Whether ancient miners intentionally designed these systems or discovered them through centuries of empirical observation remains unknown. Transportation presents another unresolved engineering puzzle. Seriphos is mountainous and steep, yet enormous quantities of ore had to be moved from inland mines to coastal loading points. Archaeologists have identified ancient transport paths cut into bedrock with surprisingly regular grooves. Some historians believe these channels may have guided sled systems or wooden carts. Others suggest lubricated wooden runners may have been used to slide heavy ore downhill, using gravity-assisted transport methods. Several routes descend at gradients that modern engineers consider unusually optimized for controlled movement of heavy loads without catastrophic acceleration. This is particularly striking because similar principles are seen in some later Roman and medieval mining operations, but are rarely documented this early in the Aegean world. The scale of labor required for the mines was also immense. Ancient records and archaeological evidence suggest Seriphos relied heavily on enslaved laborers who worked in brutal, underground conditions. In some shafts, the tunnels narrow dramatically, forcing workers to crawl through confined passages while extracting ore under dangerous conditions. Human remains and tool fragments indicate that mining accidents were likely common. The mines were not only engineering achievements, they were also places of extreme suffering that powered ancient economies through relentless extraction. What makes Seriphos especially mysterious is that much of this apparent technical knowledge seems to disappear or fragment over time. Although later civilizations continued mining throughout the Mediterranean, some specific features seen at Seriphos do not appear widely replicated at the same level of efficiency. Historians debate whether this knowledge was closely guarded by specialized mining communities, or whether the collapse of trade systems and population shifts caused entire bodies of practical engineering knowledge to vanish. What do you think really happened at Seriphos' ancient mines? Did the ancient miners of Seriphos possess engineering knowledge far beyond their time, or are modern historians still underestimating the true capabilities of ancient civilizations? Share your thoughts in the comments below. Cubba stood deep within the dry limestone hills of the Puch region in northern Yucatan, Mexico, a Maya city discovered by European explorers in the mid-19th century after centuries of abandonment beneath dense tropical vegetation. Archaeologists were immediately confused by what they found. Massive stone palaces still standing after more than 1,000 years. Thousands of perfectly shaped decorative stones fitted together with astonishing precision. Sophisticated water systems in one of the driest parts of the Maya world, and an architectural style so advanced that some researchers compared parts of it to engineered modular construction. Even today, Kaaba remains one of the most technologically mysterious cities ever built by the ancient Maya. The first large scientific surveys began in the 1840s when explorers John Lloyd Stevens and Frederick Catherwood documented the ruins in remarkable detail. Catherwood's drawings revealed entire palace walls covered in repeated stone masks of the rain god Chak. At first, archaeologists believed the structures were mostly ceremonial, but later excavations showed Kaaba had been a densely populated urban centre connected to a much larger regional infrastructure system. Modern LIDAR surveys and geological studies now suggest the city was engineered with a level of environmental planning far beyond what was once believed possible for pre-industrial Mesoamerica. One of the greatest mysteries surrounding Kaaba is the extraordinary precision of its stonework. The city belongs to the Puuc architectural tradition, famous for highly detailed mosaics and geometric facades. But at Kaaba, the level of repetition becomes almost industrial. The Qod's Poop, often called the Palace of the Masks, contains over 250 stone masks of Chak attached to its outer walls. Each mask consists of multiple carved blocks fitted together to form curved noses, symmetrical eyes, and layered geometric details. Many stones align so tightly that even modern researchers struggle to insert thin blades between the joints. This becomes more mysterious when considering the tools available to the Maya. They had no iron tools, no steel chisels, and no beasts of burden capable of transporting heavy blocks efficiently. Most carving was supposedly done using stone hammers, harder limestone, and obsidian cutting edges. Yet certain surfaces at Kaaba display flatness and angular consistency, approaching machine-like accuracy. Some blocks show repeated dimensions across different buildings, leading a few researchers to speculate that the Puuc Maya may have developed standardized stone templates or modular construction techniques centuries ahead of their time. The engineering challenge becomes even greater when examining the environment itself. Unlike many other Maya cities located near cenotes or permanent rivers, Kaaba existed in a region with severe seasonal droughts. Northern Yucatan receives roughly 900 to 1,100 millimeters of rainfall annually, but most of it arrives during only part of the year. Surface water is nearly absent due to the porous limestone bedrock. For a large city to survive here, advanced water management was absolutely essential. Archaeologists later uncovered one of Kaaba's most fascinating technological systems, underground water reservoirs known as chultuns. These bottle-shaped chambers were carved directly into limestone and coated with waterproof plaster. Rainwater from plazas, rooftops, and paved surfaces was carefully redirected through sloped channels into storage chambers below ground. Some chultuns could hold tens of thousands of liters of water. What astonished engineers was the efficiency of the design. The slope angles had to be calculated carefully enough to move water across uneven limestone terrain without losing too much to seepage or evaporation. Some reservoirs still preserve traces of hydraulic plaster after more than a millennium underground. Researchers have compared the sophistication of these systems to early urban water management technologies seen in parts of the Roman world and ancient Persia. The plaster itself remains another major mystery. Laboratory analysis suggests the Maya heated limestone at extremely high temperatures to produce lime mortar strong enough to survive tropical humidity for centuries. Some sections of Puuc masonry show unusual resistance to biological erosion despite constant exposure to roots, fungi, moisture, and acidic rain. Scientists studying ancient mortars have compared certain Maya mixtures to Roman volcanic concrete because both appear unusually durable compared to many later historical materials. Even more puzzling is how Kaaba's buildings maintain structural stability despite their construction style. Unlike Egyptian pyramids or Roman concrete domes, Puuc buildings often relied on relatively thin outer stone veneers surrounding rubble cores. In theory, many of these structures should have collapsed long ago after internal deterioration, yet several major facades remain standing with surprising integrity. Modern structural analysis suggests Maya builders may have understood sophisticated load distribution principles. Certain arches and corners use gradual stone size variation to redirect pressure away from weak points. Corbel vaults inside Kaba's palaces were designed so weight compressed inward rather than downward directly onto entrances. Similar stress distribution concepts appear in much later medieval stone architecture in Europe, yet the Maya developed them independently centuries earlier. Another unexplained feature is the Sakbi system connecting Kaaba to nearby Maya cities, especially Uxmal. A raised white limestone road stretches roughly 18 kilometers between the two cities. Archaeologists estimate enormous labor would have been required to level terrain, transport stone, and maintain the elevated roadway through dense tropical conditions. The road was not simply functional infrastructure. Its reflective white surface likely glowed under moonlight, suggesting ceremonial or astronomical significance. Some researchers believe the Sakbi functioned as a political symbol demonstrating centralized regional authority. Others argue its alignment may have had ritual or celestial meaning connected to Venus cycles or seasonal movement patterns important in Maya cosmology. Kaaba also contains evidence of surprisingly advanced urban planning. Buildings were not randomly positioned. Many align with solar directions or seasonal light events. The arrangement of plazas appears designed to maximize runoff collection during heavy rains while reducing erosion during storms. Certain elevated structures were strategically positioned to improve airflow and reduce heat accumulation in the humid, tropical climate. This environmental adaptation becomes especially impressive when compared to many later colonial settlements in the same region that struggled with water shortages and heat management despite possessing metal tools and imported European engineering knowledge. One of the darkest mysteries surrounding Kaaba is its sudden decline. The city flourished between roughly 600 and 900 CE during the late Classic Maya period. Then, within a relatively short historical window, major construction stopped and the population collapsed. Unlike some other Maya centers, Kaaba does not show widespread evidence of catastrophic warfare or complete structural destruction. Climate studies from lake sediments across the Yucatan indicate severe drought cycles struck the Maya world between the 9th and 10th centuries. Some droughts may have reduced rainfall by as much as 40% for extended periods. But this explanation alone creates another mystery. Kaaba was already specifically engineered for water scarcity. If any Maya city should have resisted drought, it may have been Kaaba. Some archaeologists believe the collapse was caused not by a single disaster but by systemic failure. Maintaining reservoirs, roads, plaster production, and large ceremonial complexes required enormous labor coordination. Once political authority weakened, the infrastructure itself may have become impossible to sustain. Others suggest regional trade breakdowns or ecological exhaustion gradually destabilized the city. Do you think the Maya discovered engineering knowledge that modern civilization still doesn't fully understand? Share your thoughts in the comments below. Above the flat plains of southern Cambodia, Phnom Chizor was discovered by early French archaeologists in the late 19th century after dense vegetation partially concealed its upper structures. Built during the reign of King Suryavarman I in the 11th century, the temple stands roughly 130 meters above sea level on an isolated hill in Takeo province, around 50 kilometers south of modern Phnom Penh. At first glance, Phnom Chizor appears smaller than the giant Khmer monuments of Angkor, but the deeper researchers examined the site, the more it began to reveal engineering mysteries that seemed far beyond what historians once believed the Khmer Empire could achieve during that era. Unlike temples constructed on flat terrain, Phnom Chizor required enormous quantities of sandstone and laterite to be transported uphill across steep slopes. Even today, visitors must climb more than 400 stone steps to reach the summit. Archaeologists estimate that some structural blocks weigh between 500 kilograms and over 2 tons. The mystery is not simply the weight of the stones, but the precision with which they were shaped and assembled at such elevation nearly 1,000 years ago. One of the biggest mysteries surrounding Phnom Chizor is how the Khmer builders transported thousands of tons of stone to the top of the hill without modern machinery. Unlike Egypt's pyramids, which were built on relatively open desert plains, Phnom Chizor sits on steep elevated terrain surrounded by tropical soil that becomes unstable during heavy monsoon seasons. Researchers comparing Khmer construction methods with ancient Egyptian engineering note that the slope angle at Phnom Chizor would have made direct dragging extremely difficult. Some scholars estimate that moving a single 2-ton sandstone block uphill using only wooden sledges and ropes could require more than 150 labourers at once. Yet the temple contains hundreds of such stones. There is evidence suggesting the Khmer may have constructed temporary earthen ramps spiralling around the hill, similar to theories proposed for pyramid construction at Great Pyramid of Giza. However, unlike Egypt, Cambodia's tropical climate rapidly erodes soil structures. If ramps existed, nearly all physical traces may have vanished centuries ago due to rainfall, vegetation growth, and landslides. Another unexplained factor is logistics. Supplying food, water, tools, and manpower on a steep, isolated hill would have required an advanced organizational system. Historians increasingly believe the Khmer Empire possessed engineering administration capabilities far more sophisticated than once assumed, possibly comparable to Roman large-scale infrastructure coordination. The stonework at Phnom Chizor presents another major mystery. Many sandstone blocks display extremely flat surfaces and tight joints with minimal gaps between stones. Some door frames and decorative lintels show cutting precision accurate to only a few millimeters of deviation across long surfaces. This level of craftsmanship is surprising because the Khmer builders primarily used iron chisels and manual shaping tools. Experimental archaeology studies have demonstrated that shaping sandstone with traditional iron tools is possible, but achieving repeated geometric precision on hundreds of blocks would require extraordinary skill and standardization. Researchers often compare Khmer masonry with Incan stonework at Machu Picchu and the polygonal walls of Sacsayhuaman. While Khmer builders did not use the same interlocking polygon technique, they achieved similarly impressive alignment and stability using rectangular forms and layered support systems. Some archaeologists believe the Khmer may have developed specialized measurement systems based on chord geometry and astronomical orientation. Others argue that generations of accumulated craftsmanship allowed workers to refine techniques far beyond what surviving records suggest. The problem is that almost no technical manuals or construction documents from the Khmer Empire survived, leaving the true methods largely unknown. Beneath many visible sandstone surfaces lies a core material called laterite, a dense iron-rich stone formed in tropical environments. Phnom Chizor heavily relied on laterite blocks for internal foundations and support walls. What makes this material mysterious is its unusual behavior over time. Freshly extracted laterite is relatively soft and can be cut into blocks with simple tools. But after prolonged exposure to air, the iron compounds oxidize and harden dramatically. Some laterite blocks at Phnom Chizor have survived nearly 1,000 years of monsoon rains while retaining structural integrity, comparable to certain modern concretes. Modern engineers studying Khmer construction have noted that the builders appear to understand drainage exceptionally well. Water channels and hidden runoff pathways prevented rainwater from accumulating inside the hilltop structure. Without such drainage systems, seasonal monsoon erosion would likely have destabilized the temple centuries ago. This raises an important question. How much did Khmer engineers truly understand about geology and material science? Their ability to combine sandstone aesthetics with laterite structural durability suggests knowledge far more advanced than simple trial-and-error construction. Phnom Chisor was not randomly placed. The temple sits at a strategic high point overlooking the surrounding plains, with architectural axes aligned in ways that may correspond to solar movement and sacred geography. Several Khmer temples appear linked through symbolic spatial relationships. Similar alignments have been observed at Angkor Wat, where the central towers align with solar events during equinoxes. While Phnom Chisor is smaller, researchers suspect it may have functioned as part of a wider ritual landscape connected through visibility lines, pilgrimage routes, and celestial symbolism. Some historians argue that elevated Khmer temples represented Mount Meru, the sacred cosmic mountain of Hindu cosmology. Yet symbolic meaning alone does not explain the engineering practicality required to execute such projects on difficult terrain. The builders had to accurately orient structures while accounting for slope angle, foundation stability, and long-distance visibility. Even with modern surveying tools, constructing symmetrical hilltop architecture remains difficult. The fact that Khmer engineers achieved this in the 11th century continues to puzzle researchers. Although Cambodia is not located in a major seismic zone like Peru or Japan, Phnom Chisor has survived centuries of weathering, soil movement, humidity, and temperature expansion cycles. Many structures remain standing despite partial collapses and centuries of abandonment. One reason may be the flexibility of Khmer construction techniques. Unlike rigid modern concrete systems, Khmer stone structures often distributed weight through layered stacking methods that allowed slight movement without catastrophic failure. Some researchers compare this concept to earthquake-resistant approaches later seen in Incan architecture. The hill itself also creates engineering complications. Building on elevated terrain risks uneven foundation settling, especially during heavy rain seasons. Yet Phnom Chisor's core structures remain remarkably stable after nearly a millennium. This suggests that Khmer engineers possess sophisticated understanding of load distribution and terrain preparation. Perhaps the most fascinating mystery surrounding Phnom Chisor is its place within Khmer technological evolution. The temple appears to belong to a transitional phase between earlier Khmer construction and the massive engineering achievements later seen at Angkor. Certain decorative elements still resemble pre-Angkor styles, while structural systems anticipate the advanced planning later perfected at Bayon and Angkor Wat. Some historians describe Phnom Chisor as an experimental stage where Khmer architects refined techniques involving elevation, drainage, stone transport, and symbolic alignment before applying them on a far larger scale. This possibility changes how historians view the Khmer Empire. Instead of isolated monuments built independently, sites like Phnom Chisor may represent steps within a centuries-long technological development program supported by organized labor networks, engineering specialists, and accumulated architectural knowledge. What do you think was the greatest lost technology behind Phnom Chisor's construction? The transportation systems, the stone-cutting precision, or something we still haven't discovered yet? Share your thoughts in the comments below. Southeastern Attica, Greece. Archaeologists excavating the hills near the ancient silver mines of Larion uncovered the remains of Thorikos, a mining and industrial settlement that operated for more than 3,000 years. Beneath the dry rocky terrain, researchers found collapsed shafts, underground tunnels, ore washing systems, furnaces, and one of the oldest known Greek theatres. What shocked historians was not the city itself, but the scale of engineering hidden underground. Thorikos looked less like a normal ancient settlement and more like an early industrial complex centuries ahead of its time. The greatest mystery of Thorikos is its enormous subterranean labyrinth. Surveys have revealed dozens of kilometers of tunnels cut directly into hard rock, many descending over 100 meters below the surface. Some shafts are barely 50 centimeters wide, forcing miners to crawl while following tiny veins of galena, the lead ore containing silver. Modern mining engineers have questioned how ancient workers could maintain such accurate directional excavation without modern surveying tools, electric lighting, or oxygen systems. Even today, tracing narrow mineral veins underground is difficult using laser mapping and geological scanners. Yet Thorikos miners somehow followed these veins with astonishing precision. Some tunnels appear deliberately angled to intersect natural airflow currents. Archaeologists discovered vertical shafts that seem almost useless for ore transport, but highly effective for ventilation. Experiments conducted in reconstructed tunnels showed that temperature differences between upper and lower shafts could create natural air circulation similar to passive ventilation systems used in modern architecture. This has led some researchers to argue that Greek miners possessed a practical understanding of airflow dynamics long before formal physics existed. Without proper ventilation, miners would have quickly died from oxygen depletion, smoke inhalation, and toxic lead dust. The fact that the mines operated continuously for centuries suggests the system worked remarkably well. Near the mines, archaeologists uncovered massive ore washing facilities unlike anything expected from the ancient world. These installations contain channels, settling tanks, filtration basins, and carefully angled stone floors designed to separate silver-bearing minerals from crushed rock using flowing water. The engineering precision is difficult to explain. Some channels maintain gradients so consistent that modern hydraulic engineers compared them to controlled sedimentation systems. Water velocity had to remain slow enough for dense mineral particles to sink while lighter debris washed away. Researchers studying the installations found waterproof plaster coatings still partially intact after more than 2,000 years. Chemical analysis suggests the builders mixed lime with volcanic or silicate-rich materials that created unusually durable surfaces resistant to erosion and mineral corrosion. The strange part is efficiency. Ancient Athens became one of the wealthiest powers in the Mediterranean, largely because of Laurian silver production. Historical records suggest enormous outputs of silver coins, enough to finance fleets, armies, and infrastructure projects. Yet experimental archaeology indicates that traditional ancient methods should not have been capable of extracting silver at such high yields. Some metallurgical researchers believe the workers at Thorikos may have used refined processing techniques that were never fully recorded in surviving texts. Entire sections of their industrial knowledge may simply have vanished. Separating silver from lead required a dangerous process called cupellation, or had to be heated to temperatures exceeding 900 degrees Celsius while maintaining carefully controlled oxygen levels. Too little oxygen and impurities remain trapped in the metal. Too much heat and valuable silver could be lost entirely. Excavations at Thorikos uncovered furnace remains and slag deposits containing crystal formations that only develop within very narrow thermal ranges. This implies ancient metallurgists somehow maintained surprisingly stable furnace temperatures for long periods. That level of heat control is astonishing considering they had no thermometers, modern refractory ceramics, or industrial insulation. Researchers comparing the slag structures found similarities with much later Roman metallurgical systems, despite Thorikos operating centuries earlier. Some theories suggest the furnaces used highly specialized airflow channels or bellow systems, capable of creating controlled combustion environments. Others argue that generations of trial and error experimentation allowed craftsmen to recognize exact temperatures through flame color, sound, and metal behavior alone. But no surviving Greek technical text fully explains the process. The silver industry at Thorikos should have consumed unimaginable quantities of wood. Cupellation requires intense and prolonged heating, meaning thousands of furnaces operating over centuries would have devoured forests across Attica. Researchers estimating fuel consumption concluded that millions of trees may have been required to sustain the industry. Yet paleo-environmental studies around Lorion do not perfectly match the scale of deforestation expected from such industrial activity. This contradiction has become one of the site's strangest mysteries. Did ancient metallurgists develop furnaces far more fuel-efficient than historians assume? Did they use charcoal production methods now lost to history? Or did they exploit alternative combustible materials not yet identified archaeologically? No explanation fully resolves the discrepancy. Evidence from Greenland ice cores revealed unusually high atmospheric lead pollution during periods of peak Greek and Roman silver production. Scientists detected spikes in airborne lead particles dating precisely to the era when Lorion mines were most active. This means Thorikos was not a small mining settlement. It was part of one of the largest industrial pollution events in the ancient world. The consequences must have been devastating. Lead poisoning affects memory, coordination, fertility, and behavior. Miners, smelters, and even nearby populations were likely exposed to toxic contamination for generations. Some historians believe the economic power of Athens may have been built partly on a hidden human catastrophe occurring beneath the ground. Thousands of enslaved workers labored in suffocating tunnels surrounded by toxic dust and furnace smoke. Ancient writers occasionally described Lorion miners as ghost-like figures emerging from underground darkness covered in ash and metal residue. The descriptions sound disturbingly similar to workers from 19th century industrial coal mines. Thorikos and Lorion may have directly changed world history. In 483 BCE, a massive silver discovery in the mines allowed Athens to construct approximately 200 triremes, advanced warships that formed the backbone of the Greek fleet during the Battle of Salamis in 480 BCE. That battle stopped the Persian invasion and preserved the independence of Greek civilization. Without Lorion silver, classical Athens may never have become the center of philosophy, democracy, mathematics, and art. In other words, the intellectual foundations of Western civilization may have depended on an underground industrial machine powered by mining technology still not fully understood today. One of the most disturbing mysteries surrounding Thorikos is how little technical documentation survived. The Greeks recorded philosophy, geometry, politics, and astronomy in extraordinary detail. Yet the engineering methods behind Lorion's mining empire remain strangely absent. Many historians suspect the knowledge was transmitted orally between skilled craftsmen and mining specialists rather than written openly. Once the mines declined, entire generations of industrial expertise may have vanished forever. This pattern appears repeatedly throughout ancient history. Complex technologies emerge, operate successfully for centuries, and then disappear almost without explanation. Roman concrete survived underwater for 2,000 years before modern scientists understood why. Damascus steel vanished despite its legendary strength. Greek fire burned on water, yet its formula was lost. Thorikos may belong to the same category, a forgotten technological system whose full capabilities disappeared long ago. What do you think the miners of Thorikos were really searching for deep beneath the earth? Silver alone, or something far more mysterious? Share your thoughts in the comments below. Buried within the dense forests of Campeche in southern Mexico, Hochob Archaeological Zone remained concealed beneath vegetation for centuries before modern archaeological surveys began documenting the site in the 20th century. The name Hochob roughly translates to place of the ears of corn, yet the city became known for something far more mysterious. Massive stone temples decorated with giant monster-like facades, unlike almost anything else in the Maya world. Unlike famous Maya centers such as Chichen Itza or Tikal, Hochob was built inside remote tropical terrain with no major rivers nearby and no obvious transportation network capable of supporting large-scale construction. Yet archaeologists discovered multi-room palace structures, ceremonial buildings, vaulted corridors, and enormous decorative facades constructed with astonishing precision. The deeper researchers investigated the site, the more Hochob began to look less like a forgotten jungle ruin and more like a technological puzzle left behind by the ancient Maya. The most iconic structures at Hochob are the enormous zoomorphic temple entrances, gigantic stone masks representing supernatural beings whose mouths form the doorway into the temple itself. These facades are composed of hundreds of carefully shaped limestone blocks fitted together with remarkable accuracy. What makes this mysterious is the level of precision achieved without iron tools, steel blades, cranes, or modern measuring equipment. Some joints between stones are so tight that even thin blades struggle to slide between them. Engineers comparing the stonework to later medieval masonry have noted similarities in precision, despite the Maya lacking metal-cutting technology available in Europe centuries later. The limestone used at Hochob is softer than granite, but that alone does not explain the consistency of the cuts. Researchers examining the surfaces discovered evidence of repeated abrasion polishing and controlled shaping techniques that would have required enormous labor coordination. Even more puzzling, many decorative sections appeared geometrically symmetrical across large surfaces, implying the builders possessed advanced planning systems and standardized measurement methods. Several archaeologists have suggested the Maya may have used chord-based geometric grids or proportional systems similar to those later documented in other ancient civilizations. Yet no surviving written technical manuals from the Maya world explain how such massive symbolic facades were designed and assembled so accurately in dense jungle conditions. One of the strangest engineering mysteries at Hochob involves its surviving stucco surfaces. Tropical environments are among the worst possible places for exposed limestone architecture. High humidity, seasonal rainfall, heat, biological growth, and expanding tree roots rapidly destroy exposed structures. In many tropical regions, unprotected stone can degrade severely within centuries. Yet parts of Hochob's stucco decoration have survived for over 1,000 years. Scientific analysis of Maya lime plaster from sites across the Yucatan Peninsula revealed evidence of sophisticated material processing. To produce lime plaster, the Maya heated limestone to temperatures approaching 800–900 degrees Celsius before mixing it with water and additives. Maintaining such temperatures consistently would have required highly organized fuel systems and advanced control of combustion environments. Researchers studying Maya plasters discovered traces of organic compounds, plant extracts, and mineral particles that may have improved water resistance and structural durability. Some modern materials scientists compare these mixtures to experimental self-healing lime mortars, where microscopic chemical reactions allow small cracks to reseal over time through calcite recrystallization. At Hochob, the survival of detailed carvings despite centuries of tropical storms suggests the builders understood environmental engineering at a surprisingly advanced level. Some walls appear capable of shedding water efficiently due to subtle surface angles invisible at first glance. Others show evidence of layered finishing techniques designed to reduce moisture penetration. The mystery becomes even greater when compared to many later colonial structures in tropical America, that deteriorated far more rapidly despite access to metal tools and later construction methods. Modern engineers consider tropical limestone terrain extremely difficult for long-term heavy construction. The porous bedrock absorbs water, fractures easily, and shifts over time. Yet Hotjob's buildings remained standing through centuries of storms, erosion, and environmental pressure. Archaeological surveys suggest the Maya may have constructed multi-layered foundations using compacted rubble, crushed limestone, and drainage materials to distribute weight across unstable ground. This resembles principles used in modern geotechnical engineering. What astonishes researchers is the scale of the achievement. Some structures at Hotjob weigh thousands of tons collectively, yet they show surprisingly limited subsidence compared to expectations for tropical terrain. Without reinforced concrete, steel frames, hydraulic excavation equipment, or modern soil analysis, the Maya somehow created stable ceremonial complexes capable of surviving for centuries. Comparisons are often made to other ancient civilizations that mastered difficult terrain, such as the Inca foundations at Machu Picchu or Roman harbour engineering along the Mediterranean. But unlike the Romans, the Maya worked without limpozzolana concrete capable of hardening underwater. Unlike the Inca, Hotjob existed in humid jungle conditions that accelerate structural decay dramatically. This raises a disturbing possibility. The Maya may have possessed generations of accumulated empirical engineering knowledge far beyond what survives in the archaeological record. Hotjob also contains large corbel-vaulted chambers, a hallmark of Maya architecture. Unlike true arches, corbel vaults are formed by stacking stones progressively inward until they nearly meet at the top. Structurally, this method creates enormous lateral pressure and instability. At Hotjob, some vaulted corridors appear unusually wide relative to their supporting walls. Modern structural simulations suggest several chambers approach dangerous load thresholds if constructed purely through basic trial-and-error methods. And yet many of these corridors survive for centuries. This suggests Maya architects deeply understood weight distribution, compression forces, and structural balance even without formal mathematical physics. Some researchers believe Maya builders refined their techniques over generations through repeated experimentation across cities in the Pus and Chens regions. The precision becomes especially mysterious considering the environmental conditions. High humidity weakens mortar, biological growth damages joints, and seasonal thermal expansion stresses stone structures continuously. Even so, parts of Hotjob's vaulted architecture remain intact long after many younger historical buildings collapsed elsewhere in the world. Several structures at Hotjob appear aligned with solar events, especially equinox and solstice positions. This is not unique among Maya cities, but the consistency of the orientations has generated debate among archaeologists. The Maya possessed one of the most advanced astronomical traditions in the ancient world. They accurately tracked Venus cycles, solar years, eclipses, and complex calendar systems. However, the precision implied at sites like Hotjob raises difficult questions. How did observers in dense jungle terrain achieve such consistent alignments without telescopes or precision optics? Some theories suggest the Maya established long-term observational stations using horizon markers and repeated generational measurements. Others argue they may have used architectural sightlines integrated into ceremonial spaces. Comparisons are often drawn to solar alignments at Stonehenge or the astronomical planning of ancient Egyptian temples near Karnak. Yet Hotjob's alignments were achieved in a tropical environment where vegetation growth constantly obstructed long-distance visibility. This makes the consistency even more difficult to explain. Perhaps the greatest mystery surrounding Hotjob Archaeological Zone is logistics. The city was built deep inside tropical jungle with no major rivers nearby. while the Maya did not use large draft animals or practical wheeled transport for massive construction projects. Yet thousands of tons of stone were still quarried, moved, and assembled into enormous structures. Simply transporting multi-ton limestone blocks through hot, humid jungle conditions would have required extremely complex labor coordination. Researchers estimate that major Maya cities demanded millions of labor hours to complete large construction projects. The real mystery is not only how the Maya built Ho-Chob, but how they maintained such a precise logistical system in one of the harshest environments imaginable. Do you think the Maya truly possessed engineering knowledge far beyond what history tells us? Share your thoughts in the comments below. Wat Ek Phnom rises from the flat floodplains of northwestern Cambodia, like the remains of a civilization that understood engineering far beyond what historians once believed possible. Archaeologists first documented the temple during French colonial surveys in the late 19th century, but its true complexity only became clear after structural and geological studies revealed something strange. This massive stone monument had survived nearly 1,000 years on unstable tropical soil that should have caused catastrophic collapse centuries ago. Built during the 11th century under the Khmer Empire, Wat Ek Phnom is often overshadowed by Angkor Wat, yet many researchers now believe it may preserve clues about forgotten construction techniques, material science, and environmental engineering that remain only partially understood today. The first mystery begins beneath the temple itself. Battambang sits in a region heavily affected by seasonal flooding, groundwater movement, and soft alluvial sediments. Modern engineers know that constructing multi-thousand-ton stone structures on such terrain is extremely dangerous without deep foundations or reinforced stabilization systems. Yet Wat Ek Phnom has remained standing for almost a millennium despite earthquakes, monsoon cycles, root intrusion and soil movement. Excavations reveal that Khmer builders created layered laterite platforms beneath the temple, possibly designed to distribute weight across unstable ground. Laterite, an iron-rich tropical soil that hardens when exposed to air, acted almost like a primitive concrete. What shocked researchers was the density and compression of these layers. In some areas, the laterite foundation reached compressive strengths, approaching low-grade modern masonry materials after centuries of natural mineralization. The engineering becomes even more puzzling when compared to other ancient civilizations. Roman builders relied on pozzolanic volcanic concrete capable of resisting seawater for over 2,000 years. The Egyptians built pyramids on stable limestone plateaus to minimize subsidence. But Khmer architects faced one of the worst possible environments for long-term stone construction. Tropical wetlands with intense rainfall exceeding 1,300 millimeters annually. Despite this, the temple's central sanctuary remains relatively aligned. Some structural surveys suggest deviations smaller than a few centimeters across sections several meters wide. An astonishing level of stability for medieval Southeast Asian construction. The stones themselves present another unresolved mystery. Many of the sandstone blocks appear tightly fitted with minimal mortar. Some joints are so narrow that even thin blades struggle to pass between them. Historians traditionally argue that Khmer workers used iron chisels, wooden levers, and manual polishing techniques. But microscopic analysis of certain tool marks suggests repetitive abrasion patterns, more consistent with advanced sanding processes than crude hammering alone. Researchers believe quartz sand mixed with water may have been used as an abrasive cutting compound, similar to techniques proposed for ancient Egyptian granite work. However, recreating the same precision using replicated medieval Khmer tools has proven extremely difficult. Even more mysterious is the transportation problem. Some sandstone blocks used at Wat Ek Phnom weigh several tons and likely originated from quarries located dozens of kilometers away. Moving such stones through floodplains and jungle terrain without wheeled heavy machinery would have required enormous coordination. Scholars estimate that transporting a single large block could have demanded hundreds of labourers using wooden sledges, bamboo rollers, and seasonal waterways. Yet, no surviving Khmer texts explain the logistical systems behind these operations. This absence of documentation has fueled speculation that the Khmer Empire possessed organisational and engineering capabilities far more advanced than traditionally assumed. The carvings at Wat Ek Phnom deepen the mystery further. Many pediments and lintels display highly symmetrical geometric patterns and mythological scenes carved with remarkable consistency. Some decorative grooves are only millimeters deep, yet maintain clean proportions after nearly 1,000 years of erosion. Sandstone is softer than granite, but it fractures easily under uncontrolled pressure. Achieving such detail repeatedly would have required extraordinary control over carving angles and force distribution. Certain historians believe Khmer artisans may have employed proportional measurement systems or reusable geometric templates. If true, this would suggest standardized architectural mathematics operating across multiple Khmer temple sites centuries before modern surveying instruments existed in the region. The climate resistance of the structure is equally difficult to explain. Cambodia's environment is among the harshest in Southeast Asia for preserving exposed stone architecture. High humidity accelerates biological growth, while thermal expansion and acidic rainfall gradually fracture mineral surfaces. Yet many laterite sections at Wat Ek Phnom remain surprisingly durable. Scientific studies on laterite used in Khmer construction found that oxidation of iron compounds over time may create hardened outer shells that naturally protect interior material from rapid decay. In other words, parts of the temple may have slowly strengthened themselves through long-term chemical transformation. This phenomenon has drawn comparisons to Roman marine concrete, which becomes stronger through interaction with seawater crystals over centuries. In both cases, ancient builders may have unintentionally exploited chemical processes modern science only recently began fully understanding. The difference is that Roman engineering texts survived. Khmer engineering methods largely disappeared with the decline of the empire, leaving modern researchers to reconstruct fragmented clues from ruins alone. Another unresolved question involves astronomical alignment. Like many Khmer temples, Wat Ek Phnom appears carefully oriented along cardinal directions. Certain corridors and gateways align closely with solar movement during specific times of the year. Achieving this level of orientation without magnetic compasses or optical instruments would have required repeated long-term sky observations. Researchers studying Khmer architecture found that many temples across Cambodia share remarkably consistent directional patterns over distances spanning hundreds of kilometers. This suggests the existence of a standardized cosmological or astronomical surveying system. Some scholars propose that Khmer architects tracked solar shadows using fixed observation poles and seasonal horizon markers. Others argue that water reflection techniques may have helped establish visual alignment baselines, but no surviving evidence fully explains how large-scale directional accuracy was maintained across generations. The mystery becomes even greater when considering the immense labor coordination required to keep temples aligned despite uneven terrain and shifting foundations. Hydraulic engineering may hold another hidden clue. The Khmer Empire is famous for massive reservoirs and canal systems surrounding Angkor, but smaller regional temples like Wat Ek Phnom were also integrated into sophisticated water management networks. Satellite imaging and ground surveys have identified ancient moats, embankments, and channels surrounding the temple complex. These systems likely served religious symbolism, irrigation control, and flood management simultaneously. Some archaeologists believe Khmer hydraulic infrastructure was so advanced that it allowed dense urban populations to survive seasonal climate extremes for centuries. Yet this same system may have contributed to collapse. Paleoclimate studies indicate Southeast Asia experienced severe megadroughts between the 14th and 15th centuries. Tree ring data and sediment analysis suggest alternating cycles of devastating droughts and extreme monsoon flooding destabilized Khmer water networks. If true, Vatek Phnom may represent not just an engineering achievement, but evidence of how even highly advanced civilizations can become vulnerable when environmental systems exceed their ability to adapt. The temple's decline remains strangely silent. Unlike many ancient cities destroyed by invasion or fire, Vatek Phnom appears to have faded gradually. Jungle growth overtook structures, maintenance ceased, religious centers shifted elsewhere. No massive battlefield debris or widespread burn layers clearly explain abandonment. It was as if the civilization sustaining the monument slowly lost the capacity to preserve it. Do you think the Khmer Empire lost ancient engineering knowledge that modern science still cannot fully explain? Share your thoughts in the comments below. Southeastern Bulgaria hides a quiet mound known as Karanovo, where archaeologists uncovered evidence of something deeply unsettling, an agricultural society more than 7,000 years old that may have possessed construction techniques, thermal engineering, and material knowledge far beyond what should have existed in Neolithic Europe. Long before the pyramids of Egypt, before Stonehenge, before the first dynasties of Mesopotamia, people at Karanovo were building settlements that repeatedly survived fire, climate shifts, and centuries of occupation in ways researchers still struggle to fully explain. The site was first systematically excavated in the 1930s by Bulgarian archaeologist Vasil Mikov. What appeared to be a simple prehistoric mound turned out to contain one of the most important stratified archaeological records in Europe. Layer after layer revealed nearly uninterrupted occupation from approximately 6,200 BCE to 2000 BCE. The mound eventually rose more than 13 meters high, purely from human habitation debris accumulated over millennia. Archaeologists identified 7 major cultural phases now known collectively as the Karanovo culture sequence, which became one of the chronological foundations for dating prehistoric southeastern Europe. But the deeper researchers dug, the stranger the site became. One of the greatest mysteries surrounding Karanovo is the extraordinary durability of its clay architecture. At first glance, the houses appear primitive, timber frames coated with mud and clay, similar to many Neolithic settlements across Europe. Under microscopic analysis, however, many of these structures show signs of partial vitrification, a process in which intense heat transforms clay into a ceramic-like material. Some wall fragments and floors display hardness approaching low-grade fired brick, despite being over 6,000 years old. This should not have happened naturally. Experimental archaeology suggests ordinary house fires in prehistoric settlements usually reach temperatures between 500 and 700 degrees Celsius before collapsing. Yet several Karanovo samples indicate thermal exposure possibly exceeding 900 degrees Celsius. At those temperatures, clay minerals begin to undergo major structural transformations. Quartz particles expand, iron compounds oxidize differently, the material becomes significantly more water-resistant and mechanically stable. The mystery is not simply that the buildings burned. Entire ancient cities burned throughout history. The mystery is why many Karanovo structures became stronger after destruction. Researchers have proposed multiple explanations. One theory suggests accidental proto-ceramic engineering. If the builders repeatedly mixed clay with precise ratios of organic material, ash, straw, and fine sediment, then large settlement fires could unintentionally create hardened surfaces similar to kiln-fired ceramics. Another hypothesis argues the process may not have been accidental at all. Some archaeologists suspect certain structures were intentionally heat-treated, possibly through controlled burning during construction or renovation. The implications are enormous. If intentional, this would mean Neolithic Balkan societies understood thermal modification of building materials thousands of years before the widespread appearance of fired brick architecture in Mesopotamia. The oldest large-scale fired bricks in cities like generally date much later, around the 4th millennium BCE. Karanovo may represent an entirely separate technological pathway that disappeared before evolving into later monumental architecture. Even more puzzling is the moisture resistance of some surviving floors. Parts of the settlement remained structurally stable despite lying underground for more than 6 millennia in fluctuating humidity conditions. Soil analyses revealed compacted clay mixtures with unusually low permeability. Modern researchers comparing them with traditional adobe structures found some Karanovo samples resisted water penetration significantly better than expected for unfired Neolithic earth architecture. No written formula survives explaining how this was achieved. The technological anomalies do not end with construction materials. Karanovo existed during a period when the Balkans were emerging as one of the earliest metallurgical centers on Earth. Copper artifacts discovered throughout the region date to the 5th millennium BCE, placing Balkan metallurgy among the oldest known anywhere in the world. Some nearby sites associated with the broader cultural sphere produced evidence of copper smelting earlier than many regions traditionally considered cradles of civilization. This presents another difficult question. Extracting copper from ore is not a simple process. Sulfide ores require controlled oxygen flow and carefully maintained temperatures. Primitive open fires are inefficient for achieving consistent metal separation. Yet slag remains and furnace traces from the Balkan Copper Age suggest increasingly sophisticated thermal control. Certain furnace fragments show internal vitrification patterns implying prolonged exposure to high heat within semi-enclosed environments. In other words, these communities may already have been experimenting with engineered combustion systems over 6,000 years ago. Compared to later Bronze Age metallurgy, the scale was still small, but technologically the leap was massive. Humanity was transitioning from shaping stone to manipulating the atomic structure of minerals through heat. At Karanovo and surrounding Balkan settlements, that transition appears to have begun startlingly early. Another unresolved mystery involves symbolic markings discovered on pottery, ritual objects, and seals. Some symbols resemble geometric patterns found across southeastern Europe during the Vinca and Karanovo cultural phases. Certain researchers argue these signs may represent a form of proto-writing predating Sumerian cuneiform by more than 1,000 years. The debate remains highly controversial. Skeptics argue the symbols are merely decorative or religious motifs. But supporters of the proto-writing hypothesis point to repeated symbol combinations, standardized incisions, and recurring sequences across multiple sites separated by large distances. Some signs appear in nearly identical forms over centuries, suggesting a shared symbolic system rather than a random artistic expression. One artifact in particular continues to fuel speculation: the so-called Karanovo seal. Covered with arranged geometric symbols in circular formation, the object has been interpreted by different researchers as a ritual calendar, astronomical marker, ownership seal, or ceremonial device linked to agricultural cycles. Its symmetry is difficult to ignore. Some investigators noticed possible correlations between the radial divisions on the seal and lunar or seasonal intervals important for early farming societies. While no interpretation has achieved consensus, the object demonstrates an unexpectedly advanced level of abstract symbolic organization for a Neolithic culture, traditionally portrayed as technologically primitive. Trade networks connected to Karanovo create yet another layer of mystery. Archaeologists found materials that could not have originated locally, including Mediterranean shells and obsidian transported across hundreds of kilometers. Obsidian sourcing studies indicate long-distance exchange systems operating across southeastern Europe during the Neolithic period. Maintaining such networks should have been extremely difficult. This was a world without wheeled transport on a large scale, without formal states and without written contracts. Yet goods, raw materials, and possibly ideas moved across vast regions with surprising consistency. To sustain this level of exchange, communities would have needed surplus food production, social coordination, and systems of trust sophisticated enough to connect distant populations over generations. Modern depictions often portray Neolithic Europe as isolated farming villages barely surviving season to season. Karanovo tells a very different story. Do you think Karanovo was simply an advanced Neolithic settlement, or evidence of forgotten knowledge humanity completely lost thousands of years ago? Share your thoughts in the comments below. The dry hills of southeastern Attica in Mines of Lorien conceal a labyrinth so vast that modern archaeologists still cannot map all of it. More than 2,000 vertical shafts descend into the rock. Hundreds of kilometers of tunnels twist through the earth beneath Greece. Some are barely wide enough for a human body to crawl through. Yet over 2,000 years ago, these mines produced enough silver to transform Athens into the dominant power of the ancient Mediterranean. The deeper researchers study Lorien, the stranger it becomes, because this was not simply a primitive mine. In many ways, it functioned like an industrial complex operating centuries before the industrial age supposedly began. The mines were known in Iranian antiquity, but their true scale only became clear during the 19th century when modern mining companies reopened parts of the ancient workings. Archaeologists soon discovered enormous underground networks, washing facilities, furnaces, drainage systems, and ventilation shafts preserved beneath the landscape. Later geological surveys revealed that ancient miners had followed narrow silver-bearing galena veins with astonishing precision, often deep underground and across multiple levels. The first mystery is scale. Modern estimates suggest the Lorien mining district contained more than 5,000 individual mining works, approximately 2,000 shafts, hundreds of kilometers of tunnels, and extraction depths exceeding 100 meters. For comparison, many European medieval mines remained far smaller and less organized more than 1,000 years later. What shocks engineers today is not only the quantity of excavation, but the accuracy of it. The silver-bearing mineral at Lorien mainly existed in thin galena veins trapped within limestone formations. Missing the vein by even a few meters could mean excavating useless rock for weeks. Yet ancient miners repeatedly tracked these veins with extraordinary efficiency, despite having no seismic imaging, no geological maps, no explosives, no electric lighting, and no precision drilling tools. Even so, many tunnels curve almost perfectly alongside ore deposits, adapting to changes in rock direction in ways remarkably similar to modern mining logic. Some shafts intersect other tunnels with surprising precision, despite being dug from different underground levels. Researchers still debate how ancient surveyors maintained orientation inside total darkness, with only oil lamps and hand tools. Experimental archaeologists estimate that removing a single cubic meter of hard limestone using iron chisels and hammers could require dozens of labor hours. At Lorien, millions of cubic meters were excavated. This raises a disturbing possibility. The organizational and geological knowledge of the ancient Greeks, may have been far more advanced than traditionally assumed. Air was one of the deadliest problems in ancient mining. Deep underground tunnels accumulate carbon dioxide, heat, toxic dust, lead particles, and smoke from oil lamps. Even in 18th century Europe, poor ventilation killed miners regularly, yet Lorient operated continuously for centuries. Archaeologists discovered that many vertical shafts in the mines were not designed primarily for extraction. Instead, they appear positioned specifically to create airflow circulation. Some tunnels were constructed at carefully chosen gradients, while others connected multiple underground levels in ways that naturally pulled warm air upward while drawing cooler air downward. Modern airflow simulations suggest several shafts were placed in near-optimal positions for passive ventilation. This is difficult to explain through simple trial and error because moving a shaft even slightly can drastically reduce airflow efficiency underground. Yet many Lorient passages appear deliberately engineered around air movement. Ancient Greek writers never left a complete technical explanation of these systems, and that missing knowledge has become one of the site's greatest mysteries. Did miners slowly develop empirical airflow science through generations of experimentation, or did a larger body of mining engineering knowledge disappear completely from history? The region around Lorient is dry and harsh. Annual rainfall is low, and water shortages have existed there since antiquity. That makes the next discovery even more confusing. Researchers uncovered massive ore washing complexes throughout the mining district containing sedimentation tanks, stone channels, crushing floors, filtration basins, and water recycling systems. These facilities were designed to separate silver-bearing minerals from waste rock through density differences. Crushed ore was washed repeatedly so heavier galena particles settled while lighter material was removed. But the process required enormous quantities of water. To solve this problem, the ancient Greeks built highly sophisticated hydraulic systems, including large cisterns carved into rock, rainwater collection networks, settling basins, and closed-loop recycling channels. Some waterproof coatings inside the cisterns still function after more than 2,000 years. The industrial scale is staggering. At several processing sites, archaeologists estimate thousands of tons of ore could be treated annually. Entire landscapes around Lorient were transformed into interconnected mining and refining zones. This does not resemble isolated ancient workshops. It resembles an organized industrial economy operating in the classical world centuries before industrialization supposedly began. The most difficult technological mystery at Lorient begins after extraction. Silver in the mines mostly existed within galena ore, a lead sulfide mineral containing only small amounts of precious metal. To obtain silver, ancient metallurgists had to perform a dangerous and extremely delicate process known as cupellation. This required crushing the ore, smelting lead from sulfur compounds, reheating the lead inside oxygen-rich furnaces, and separating silver from oxidized lead. The process sounds simple in theory, but in reality it is extraordinarily difficult. Silver melts at approximately 962 degrees Celsius, while lead melts at only 327 degrees Celsius, and lead oxide formation depends heavily on oxygen concentration and furnace temperature. If temperatures were too low, separation failed entirely. If temperatures became too high, silver losses increased dramatically, furnaces destabilized, and fuel consumption exploded. Modern metallurgists examining Lorient slag discovered something astonishing. The remaining silver content inside ancient waste material is often surprisingly low. In some samples, extraction efficiency appears far beyond what historians expected from classical age technology. This means Lorient workers were controlling furnace environments with exceptional precision despite lacking thermometers, modern chemistry, steel temperature probes, or industrial bellows systems. Even more mysterious is the consistency. Some furnace remains indicate relatively stable heating conditions across repeated smelting cycles. Maintaining such control using charcoal fires alone would require remarkable expertise. Researchers believe Lorient metallurgists may have relied on highly refined observational methods involving flame color, sound resonance, airflow behavior, smoke density, and subtle color changes in molten lead. Essentially, they may have developed a practical thermal science entirely through experience. Experimental archaeology projects attempting to recreate ancient Greek cupellation found that even small changes in airflow could alter silver yield dramatically. In several modern reconstructions, maintaining stable furnace conditions for long periods proved extremely difficult even for trained teams with modern understanding of metallurgy. And yet, Lorient achieved production on an enormous scale. This has led some historians to argue that ancient metallurgical knowledge may have been far more sophisticated than surviving texts suggest. Because what existed at Lorient was not crude metalworking, it was precision industrial chemistry without modern scientific language. One of the most shocking discoveries connected to Lorient did not happen in Greece, it happened in Greenland. Ice core studies revealed spikes in atmospheric lead pollution dating back more than 2,000 years. Isotopic analysis linked much of that pollution directly to Mediterranean silver production, including Lorient. This means the mines produce contamination on a hemispheric scale. Ancient Athens was releasing enough lead into the atmosphere for traces to travel thousands of kilometers and become trapped in Arctic ice. Pollution levels rose during periods of intense Athenian expansion and dropped sharply during wars and economic collapse. The implication is extraordinary. Lorient may represent one of humanity's earliest examples of industrial-scale environmental impact. Long before factories, steam engines, or modern capitalism, an ancient civilization had already created pollution detectable across the planet. Do you think the ancient Greeks possessed technological knowledge far beyond what history officially recognizes? Share your thoughts in the comments below. Hatnub lies deep within the eastern desert of Egypt, roughly 20 kilometers from the Nile Valley. 4,500 years ago, workers entered this barren landscape to extract one of the most prized materials in the ancient world, Egyptian calcite alabaster. What they left behind may be one of the most important clues ever discovered about how the civilization of the pyramids truly moved massive stone. The site had been known since the 19th century, but the most shocking discovery came in 2018, when archaeologists uncovered a massive ancient ramp system carved directly into the quarry floor. At first glance, it looks simple. Then engineers began calculating its angle. The central ramp was far steeper than historians believed ancient Egyptians could realistically use to drag multi-ton blocks uphill. Along both sides were staircases lined with symmetrical holes once used for wooden posts. The arrangement suggested something extraordinary. The workers may have threaded ropes around these posts to create a primitive mechanical advantage system capable of multiplying pulling force. For decades, pyramid theories struggled with one fundamental problem. A limestone block weighing 2 to 3 tons can already require enormous manpower to move across flat ground. Some granite blocks in the Great Pyramid complex weighed more than 70 tons. Traditional models proposed long shallow ramps with gradients under 10% because anything steeper would become physically impossible. But the Hatnub ramp appears to exceed gradients of 20% in places. That changes everything. Experimental engineers studying the system proposed that teams hauling a sled could pull ropes wrapped around the wooden posts, while workers standing on the staircases acted as stabilizers. The post would reduce slippage and distribute tension more efficiently across the hauling system. In effect, the Egyptians may have created a crude but highly effective force amplification device thousands of years before classical pulley systems became widespread. Some researchers compared the concept to a capstan mechanism used in later maritime engineering. The implications are enormous. If the Hatnub system worked as intended, then ancient Egyptian labour efficiency may have been dramatically underestimated for over a century. It would mean Pyramid-era engineers possessed an advanced practical understanding of friction, load distribution, counterforce, and traction mechanics. Not theoretical mathematics in the modern sense, but applied engineering refined through generations of experimentation. Even more mysterious is the material they were extracting. Hatnub alabaster is beautiful but extremely fragile. Unlike granite, which fractures violently under force but remains structurally hard, calcite alabaster is softer and highly prone to cracking under uneven stress. Yet many surviving Egyptian alabaster vessels, statues, sarcophagi, and temple furnishings were carved from remarkably large intact blocks. Some pieces display surfaces so smooth and symmetrical that modern observers often underestimate how difficult the raw extraction process actually was. To quarry large alabaster blocks without catastrophic fractures would have required extraordinary control over pressure distribution. Copper tools alone should have worn down rapidly. Dolerite pounding stones could break material away, but uncontrolled impact risks sending invisible fractures through the stone. Modern quarry operations rely heavily on steel cutting systems, controlled vibration management, and precision separation techniques. The Egyptians had none of these, yet Hatnub produced luxury stone for centuries. Archaeologists studying extraction marks at the site noticed long linear cut traces and surprisingly controlled fracture lines. Some researchers believe quarry workers intentionally exploited the natural bedding planes of the calcite deposits with a level of geological understanding rarely associated with Bronze Age civilizations. Others argue that ancient craftsmen may have used lubrication techniques involving water or oil to reduce stress during separation. No consensus exists. Then there is the logistical problem. Hatnub sits in an arid desert environment where summer temperatures can exceed 40 degrees Celsius. Maintaining a permanent industrial operation there would have required enormous organization. Inscriptions at the quarry mention expeditions composed of administrators, scribes, stoneworkers, transport crews, and supervisors. Some expeditions likely involved hundreds of laborers operating simultaneously. This challenges the outdated image of pyramid construction as chaotic slave labor. Modern archaeological evidence increasingly points toward highly organized state-managed labor systems with food distribution, housing networks, medical care, and rotational workforce planning. At Hatnub, workers had to transport water, timber, rope, tools, and food deep into the desert, while simultaneously hauling massive stone blocks back toward the Nile. The rope technology alone raises questions. Plant fiber ropes deteriorate rapidly under desert heat and repeated heavy strain. Yet the hauling systems implied at Hatnub would have subjected ropes to extreme tension loads, potentially exceeding several tons per line. The Egyptians somehow maintained enough material reliability to operate quarry networks continuously for generations. Some surviving ancient rope fragments from Egypt demonstrate surprisingly sophisticated weaving structures, but the full engineering limits of these materials remain poorly understood. The desert roads surrounding Hatnub add another layer of mystery. Satellite analysis and archaeological surveys suggest that many quarry routes were not random tracks worn into the landscape, but carefully selected transport corridors optimized to minimize slope variation and maintain sled stability. Certain road segments appear intentionally reinforced with compacted surfaces. In some areas, ancient workers may even have modified terrain to improve transport efficiency. This aligns with another controversial discovery connected to Egyptian transport technology. Tomb paintings from the 12th dynasty depict workers dragging colossal statues on sleds while another individual pours liquid in front of the sled runners. In 2014, physicists from the University of Amsterdam demonstrated experimentally that slightly wet sand can reduce drag force significantly by increasing the rigidity of the sand surface. Under ideal moisture conditions, pulling resistance may drop by nearly 50%. Combined with the Hatnub ramp system, this suggests Egyptian engineers were not relying on brute strength alone. They may have systematically manipulated environmental physics to move impossible loads with maximum efficiency. And yet major questions remain unanswered. Why is physical evidence for similar ramp systems so rare if they were essential to pyramid construction? Why do many reconstructed pyramid theories still fail to account for the speed at which massive royal complexes were completed? The Great Pyramid alone contains an estimated 2.3 million stone blocks. Even assuming a 20-year construction period, workers would have needed to position roughly 300 blocks per day. Some researchers argue the logistics border on industrial-scale production. Hatnub may provide a missing piece of that puzzle. Instead of imagining pyramid construction as primitive labor amplified by sheer manpower, the evidence increasingly points toward a civilization that mastered practical engineering through observation, repetition, and incremental optimization over centuries. Their systems were not powered by advanced machines in the modern sense, but they may have been far more mechanically sophisticated than traditional history once allowed. The quarry inscriptions also reveal something psychologically important. Many workers left behind names, expedition records, prayers, and statements of achievement. These were not anonymous masses blindly hauling stone. They were organized specialists participating in state engineering operations on a scale unprecedented in the ancient world. Do you think Hatnub finally explains how the pyramids were built? Or does it prove the ancient Egyptians possessed engineering knowledge far beyond what historians still accept? Share your thoughts in the comments below. Copper was not supposed to exist here. Not this early. Not in a small Neolithic settlement hidden in the hills of eastern Serbia. Yet beneath the soil of Belovode archaeological site, archaeologists uncovered evidence that humans were extracting metal from stone nearly 7,500 years ago, more than 1,000 years before the rise of the first Great Bronze Age civilizations. The discovery forced historians to question one of the oldest assumptions in archaeology, that advanced metallurgy began in the Near East and slowly spread into Europe afterward. Belovode was excavated as part of research into the mysterious Vinca culture, a Neolithic civilization that existed across the Balkans between roughly 5,700 and 4,500 BCE. During excavations, researchers discovered fragments of copper slag, furnace debris, burned ore, and vitrified clay surfaces. Radiocarbon dating placed some of the material around 5000 BCE. At first, many archaeologists assumed contamination or natural burning, but laboratory analysis confirmed something astonishing. The inhabitants were intentionally smelting copper ore. That date changed everything. Before Belovode, the standard timeline placed the birth of metallurgy in Anatolia and Mesopotamia around the late 5th or 4th millennium BCE. Belovode pushed organized copper smelting significantly further back in time and deep into prehistoric Europe. The greatest mystery surrounding Belovode is not simply that copper existed there. It is that the people living at the site appear to have understood a highly complex industrial process, long before historians believed such knowledge was possible. Melting pure native copper is relatively simple, and small pieces can accidentally melt inside pottery kilns. But Belovede shows evidence of something far more advanced, extracting copper from ore through controlled smelting. That process is enormously more difficult. Copper ores such as malachite or azurite must be heated to temperatures exceeding approximately 1080 degrees Celsius. Reaching that heat consistently in the Neolithic period should have been extremely challenging because ordinary open fires cannot maintain such temperatures for long, and even many early furnaces from later periods struggled with thermal stability. To achieve this, the Vinca people needed a furnace capable of retaining extreme heat, controlled oxygen flow, proper charcoal-fuel ratios, knowledge of ore preparation, and timing precise enough to separate metal from waste material. This is what makes Belovede so controversial. Archaeologists are not looking at a lucky accident. They are looking at a technological system. Compared to other Neolithic communities in Europe, the gap is staggering. Many settlements from the same period were still using polished stone axes and bone tools almost exclusively, while Belovede's inhabitants were experimenting with pyrotechnology sophisticated enough to alter the atomic structure of rock. Even more confusing is how suddenly the technology appears. Normally, industrial innovation develops gradually over centuries. Pottery becomes hotter, kilns improve, experiments increase, and metallurgy slowly emerges. But at Belovede, the evidence suggests people already understood the fundamentals surprisingly early. The transitional stages are largely missing. Some researchers compare this leap to finding a functional steam engine in a medieval village centuries before the Industrial Revolution. One of the most disturbing technical mysteries involves the furnaces themselves. Fragments of clay found at Belovede show signs of vitrification, a transformation where clay partially melts into a glass-like substance due to prolonged exposure to extreme heat. In some areas, the thermal damage suggests temperatures exceeding 1,100 degrees Celsius. That raises an uncomfortable question. How were Neolithic people controlling heat with such precision? Most reconstructions of primitive furnaces struggle to maintain those temperatures consistently without advanced airflow systems, yet no surviving bellows, metal pipes, or mechanical air systems have been found at Belovede. Some archaeologists believe the Vinca may have used underground draft furnaces, while others propose natural wind tunnels built into hillside structures. A few experimental archaeologists managed to reproduce similar temperatures using carefully engineered clay furnaces combined with charcoal and ceramic air nozzles. But these experiments required extraordinary precision and repeated failures. In other words, Belovede's metallurgy may have depended on generations of accumulated technical knowledge that left almost no trace behind. The mystery becomes even deeper when compared to Egypt. Around the same period, Egyptian communities were still primarily working with stone, flint, and limited ornamental copper. Large-scale controlled smelting would not dominate the region until much later. Yet in the Balkans, an apparently isolated Neolithic society was already manipulating ores at industrial temperatures. Chemical analysis of slag and ore fragments revealed something remarkable. The people of Belovede did not use random stones. They selected specific copper-rich minerals with unusually high efficiency. Many samples contain malachite and azurite, minerals identifiable by their bright green and blue coloration, but color alone does not explain the sophistication of the process. The ore was often crushed into smaller particles before heating. This dramatically improves oxygen exposure during smelting and increases metal extraction efficiency. That detail matters because it suggests an understanding of process optimization rather than primitive experimentation. Researchers also discovered that some ore sources likely came from locations several kilometers away. This implies organized mining expeditions or trade networks capable of transporting heavy mineral loads. The Vinca culture may have possessed one of the earliest specialized resource economies in Europe. That possibility changes the image of Neolithic societies entirely. Rather than isolated farming villages, Bellovode may represent a proto-industrial community where certain individuals specialized in metallurgy while others managed agriculture, transport, or construction. Another disturbing clue emerged from environmental studies around the region. Sediment analysis revealed elevated concentrations of heavy metals consistent with prolonged copper smelting activity. Tiny traces of contamination appear embedded in ancient soil layers dating back thousands of years. This suggests Bellovode was not conducting occasional experiments. The process may have operated repeatedly for generations. If true, the site could represent one of humanity's earliest examples of industrial environmental impact. The implication is extraordinary. 7,000 years before factories darkened the skies of 19th century Europe, prehistoric metallurgists in the Balkans may already have been altering local ecosystems through chemical pollution. Some scientists argue the scale was still small compared to later Bronze Age operations, but the principle remains the same. Humans had begun transforming the environment through industrial heat and metallurgy far earlier than expected. The Vinca civilization remains one of the great mysteries of the Neolithic world. Their settlements were unusually large for the time, with some containing thousands of inhabitants, along with strange symbols carved into pottery that many researchers believe may represent a form of proto-writing. But by the end of the 5th millennium BCE, many Vinca settlements declined or were abandoned. Metallurgical activity decreased, trade networks collapsed, and much of their technological knowledge appears to have vanished with them. This creates one of Bellovode's biggest mysteries. How could such advanced metallurgical knowledge disappear? Some researchers believe copper smelting consumed enormous amounts of charcoal, leading to severe deforestation. Others point to climate change or social collapse. But another possibility is even more unsettling. The knowledge may have belonged only to a small group of specialist metalworkers, and when they disappeared, the technology disappeared with them. What do you think happened to the lost metallurgical knowledge of the Vinca civilization? Was it destroyed by collapse, forgotten over time, or hidden within a small group of ancient specialists? Share your thoughts in the comments below.